Good morning, everyone. Before we start, I want to take a minute and remind everyone the schedule for this morning's session, which I also just posted on the general Slack channel. So this is just a screenshot from the detailed schedule PDF, which you can find on the website. So we are starting with a short 2 talks, half-an-hour session about stellar astrophysics, which will be immediately followed by our first Splinter sessions. You can see here the list of the session and the room number and the Zoom links. The links are not clickable on the screenshot, of course, but they are clickable in the PDF. Sorry about that. They are clickable in the PDF file on the website. So we will start with the first talk in the stellar astrophysics. It will be by Trevor Dorn-Wallenstein. Hope I pronounced that correctly. Trevor prefers that we will do it through a recorded talk. So I will start the recording. And again, the questions will be in the Stellar Astrophysics Slack channel. So let's start.
Hey everyone, thank you so much for joining me, and thanks to the SOC for putting on a tremendous conference and allowing me to share.
Can you see my, can you see the screen, the video itself?
Yes, it just needs to go to full screen.
Okay. Because for some reason I cannot see it, but that's okay.
There are some really cool results that my collaborators and I have been finding looking at evolved massive stars with TESS. Now, the evolution of massive stars is highly uncertain, and this uncertainty comes from 2 different places. Observationally, it comes from the fact that massive stars are quite rare, both due to the initial mass function and due to their quite short lifetimes. As a result, our sample sizes tend to be quite small, and our uncertainties tend to be quite
Avi,
large.
we're actually just seeing
on the theoretical end
the
of
black
things,
screen
tiny
right now.
yet physically plausible variations.
Sorry about that.
You might need to just try resharing.
Stop sharing and screen share again.
And try to share QuickTime itself.
That's exactly what I'm trying.
Great.
Hey everyone, thank you so much for joining
Better?
me, and thanks to the SOC for putting on a tremendous conference and allowing me to
still a
share
black
some
screen.
really cool results that my collaborators.
Screen. Sorry about that.
If need be, I can share my screen and give the talk, although it'll be somewhat less enthusiastic.
That might be better. Sorry about that glitch.
Don't worry.
Trevor, do you have the recorded video? Because we could try having you share it instead in case that makes a difference.
I do, as a matter of fact. Let's see. Let's try that. Can everybody see that?
Yeah, that looks good.
Awesome. Hey everyone, thank you so much for joining me, and thanks to the SOC for putting on a tremendous conference and allowing me to share some really cool results that my collaborators and I have been finding looking at evolved massive stars with TESS. Now, the evolution of massive stars is highly uncertain, and this uncertainty comes from 2 different places. Observationally, it comes from the fact that massive stars are quite rare, both due to the initial mass function and due to their quite short lifetimes. As a result, our sample sizes tend to be quite small, and our uncertainties tend to be quite large. On the theoretical end of things, tiny yet physically plausible variations in the way that we treat stellar evolution leads to drastically different evolutionary pathways once a model has left the main sequence, making it especially difficult to compare models with observations. This means that rather than a quantitative picture of stellar evolution, we're left with this qualitative picture that we call a Conti scenario that predicts the trajectory through various evolutionary phases that a star takes as a function of its initial mass. And I want to draw your attention to this kind of intermediate branch in the Conti scenario, where stars between about 25 and 40 solar masses begin their lives as O stars, cross the HR diagram to become red supergiants, and then are able to lose a good chunk of their envelopes through stellar winds before crossing the HR diagram again and exploding. Now, TESS is really amazing for studying evolvements of stars. Before TESS came along, our ability to study the high frequency variability in evolved massive stars was more or less non-existent. Sure, we had individual studies of small numbers of evolved massive stars, but really it's thanks to TESS's all-sky coverage that we're now able to get very rapid cadence data for dozens, if not hundreds, of evolved massive stars for the first time. And of course, anytime you look at something in a new way, whether that be a new wavelength or frequency regime or with new sizes of samples, we're going to see stuff that is cool and weird and awesome. Now, before I get into the cool, weird, awesome stuff we found, one final piece of context. So remembering that kind of intermediate branch of the Conti scenario where these 25 to 40 solar mass stars become red supergiants, then lose their masses before exploding, this implies that if we look at the progenitors of type 2p supernovae, that is, stars that explode as red supergiants, we should see progenitor masses between about 8 and 25 solar masses. But that's not what we see. We actually see an upper limit of about 17 to 20 solar masses, above which stars don't explode as red supergiants. And there's a few solutions to this red supergiant problem. One is that maybe we just don't understand how explosions work. Some of these stars might be imploding rather than exploding. Maybe we just need better statistics. We need to observe more supernova progenitors. Or maybe, and this is my preferred solution, maybe we just need to get a better handle on mass loss. Maybe these 20 to 25 solar mass stars are losing a good chunk of their envelopes, either through strong stellar winds or through eruptive events before they evolve bluewards on the HR diagram to explode as yellow or blue supergiants. So this raises the problem. How do you distinguish between a yellow supergiant that's evolving across the HR diagram for the first time and one that's already been a red supergiant and is evolving bluewards? Well, maybe you can actually go and look for material that had been ejected during the previous red supergiant phase, like we can see here in the Runny Egg Nebula. If you can't directly resolve that material, maybe you can look for the infrared excess that is a signature of this material, but both of these methods rely on the fact that the CSM should be detectable. If it's not, we can start looking for surface abundance enhancements that would tell us that a star had gone through a previous fully convective phase. But this requires high resolution data and reliable models. The method that I prefer is to look for pulsations. So what I'm showing here in this top panel is a 25 solar mass model evolving from left to right, from higher to cooler temperatures. And all of these X's show modes that are not excited in this model. And so as the star crosses the HR diagram, few to no pulsations are excited. However, after the star experiences significant mass loss and starts evolving now from the right to the left on this bottom panel, we see that the landscape of possible modes becomes a lot more complex and a lot more modes are excited, shown as filled circles in this bottom plot. Which means that if we want to look for post-red supergiant objects, we should look for pulsating supergiants. Of course, this is where TESS comes in. Thankfully, the Large Magellanic Cloud is in TESS's southern continuous viewing zone, and yellow supergiants in the LMC have the perfect brightness to give us really high precision markers. So this is kind of the region in the HR diagram we were looking at, and to ground us a little bit, I'm going to show the astroseismic HR diagram. We're up here in kind of this top right corner. where the Stephan stability strip is down in the bottom right of this plot, and the yellow void, which is a region where very luminous yellow supergiants, their atmospheres can go dynamically unstable and do some weird things, is up at the top. To give us a mass scale, I'm going to show some evolutionary tracks that I computed using MESA. And now I'm going to show our sample here in the HR diagram, but I'm showing it in kind of a weird way. I'm showing each star's periodogram from the TESS data at the star's location in the HR diagram. What we see is that all of these periodograms show this characteristic rising power at low frequencies, or stochastic low frequency variability that we heard a lot about yesterday in Dorn-Wallenstein's talk, and we'll hear more about later in the week from Matteo Cantiello. Now, this stochastic variability is also ubiquitous in O and B stars, where it's been contributed either to internal gravity waves or to subsurface turbulent convection. And while the cause of the stochastic variability in the yellow supergiants is unknown, either one of these options would make a really neat diagnostic of what's going on beneath the surface in these stars that are approaching the ends of their lives. Now, if we fit the shape of the stochastic low frequency variability and divide that shape out, we get this, where we can see two clear groups of pulsators that I'm now going to highlight in blue and green. The blue stars are a known class of pulsating variable. These are alpha Cygni stars, which for a while were posited to be possible post-red supergiant objects, but as you can see here, their luminosities and therefore their masses are all a little bit too low. We don't expect a 15 solar mass star to be able to lose enough of its envelope to cross across the HR diagram again. The second group of stars that I'm highlighting in green is a brand new class of pulsating supergiant that we're calling fast yellow pulsating supergiants. Now, the exciting thing about these FIPS is that they're all about 17 to 20 solar masses, which, if you recall, is that upper limit above which stars don't explode as red supergiants, making FIPS a really exciting post-red supergiant candidate. Now, we've gone a little bit further with these objects, but I just want to say really quick that this is preliminary work, so please do not put this on Twitter or any other social media. In the year since that we discovered FIPS, TESS has allowed us to significantly expand our sample of stars. So we've gone from an HR diagram that looks like this to now here, where I'm showing the periodograms after dividing out the stochastic low frequency variability for 201 stars. Now, about half of these stars that I'm showing as the dark black periodograms have light curves from which we're able to extract at least one frequency with statistical significance, which is just wild. If half of these stars are pulsating, that's a lot. So to kind of assess what's going on, we can ask ourselves, where in this diagram do the pulsators live? So that's what I'm showing in the top right corner, which shows a two-dimensional histogram of where the pulsators live. And we can divide this plot by a two-dimensional histogram of where the overall sample lives to show the fraction of pulsating stars as a function of effective temperature and luminosity, with yellow corresponding to a high fraction of pulsators. What's interesting is that there is structure in this plot, and we can do some statistical tests to assess whether or not this structure is real. So in this plot, blobs that are in dark green are statistically significant overdensities of pulsators, and blobs in dark purple are statistically significant underdensities. Once again, we see two clear groups of pulsators, this vertical strip of alpha Cygni variables here at about 10,000 Kelvin, and this box that I've outlined in the red square here that are the fast yellow pulsating supergiants. And I'm showing the original 5 FIPS from that we discovered last year as black stars. Now that we know kind of a little bit better what region of the HR diagram these FIPS live in, we can turn to evolutionary models. And with these models, we find that the observed fraction of pulsating stars in that red box in both the small and large Magellanic Cloud is consistent with predictions for the fraction of partially stripped stars in this box in 2 different sets of evolutionary models, the BPAS models in blue and the Geneva models in orange. What's really neat is that looking at the BPAS models, we don't see a significant difference between the behavior of the single stars and the binary stars, implying that binary interactions don't play a strong role in the evolutionary history of FIPS. Okay, so to summarize, we find that stochastic low-frequency variability is a ubiquitous property of massive stars from all the way from the beginnings through the ends of their lives. And though I didn't get a chance to talk about it a whole lot, I'm happy to answer any questions on it. We also confirm the existence of fast yellow pulsating supergiants as a new class of pulsator, and we use some evolutionary models to find some compelling indirect evidence that FIPS are the partially stripped descendants of about 17 to 25 solar mass stars. Finally, I'm going to be on the postdoc job market this fall. And so if you're interested in chatting with me about any of this work, any of the other work that I do, or you just want to see some really cute pictures of my dog, I'm going to leave my contact information up here and take any questions that you might have. Thanks.
Thank you. And we have time for maybe one or two questions. Simon Murphy is asking, some of your stars are crossing the Cepheid instability strip, of course, but not all of those appear to be Cepheids. Is that something you expect? And for the ones that are Cepheid, do the pulsations allow more detailed characterization?
Yeah, so that's a really good question. So the neat thing about, and I can, let's see, I can share my screen and go back to this plot here. Let's see. There we go. Okay. So the really interesting thing that we see is that looking at this plot, there's actually an underdensity of pulsators in our sample right at the Cepheid instability strip. And what that says to me is that you know, these pulsations in these Cepheids, which are on kind of longer timescales than what we're looking at, aren't getting picked up at these high frequencies, right? Because a lot of them kind of get smoothed out in the 2-minute data, at least I think they do. And so that's telling me that throughout this entire sample, we're not actually seeing low frequency variability that's kind of bumped up into these, you know, day or faster periods that we're observing just through systematics. And so we're not just seeing that. And let me remind myself what the second half of your question was. And for, yeah, I have not looked at the pulsating stars in this part of the diagram yet to see whether or not we can actually see what's going on with them. No.
Yeah, I think I know what Simon wants to use those pulsations for. Okay, if there are any other questions, please use the Stellar Astrophysics channel, and Trevor, please go to that channel to answer any other questions or to continue that discussion with Simon. We will move to the next talk by Ingrid Pelisoli. Ingrid, please share your screen and go ahead.
Thanks. Hopefully you can see that.
Yeah, yes, we can.
Okay, perfect. Let me just move this away. Okay, I'll just go ahead then. Oops, sorry. Hello everyone, my name is Ingrid Pelisoli. I'm a research fellow at the University of Warwick in the UK. And today I'm going to talk to you about an exciting discovery that myself and my collaborators, who are listed down here, have made using TESS data. This discovery was a system called HD 266435, which qualifies as a supernova 1A progenitor. Supernova 1A are not the ones resulting from massive stars like the ones Trevor was talking about. They are the ones that are believed to result from a thermonuclear detonation in a white dwarf that has reached the Chandrasekhar mass limit. These are very bright explosive events that can be used as standard candles, and because of that, we can use them to estimate cosmological distances, allowing us to measure, for example, the expansion of the universe. There are two main channels leading to supernova 1A, the double degenerate channel, which is illustrated here in the left panels. In this channel, what happens is that two white dwarfs merge, and through this merger, they reach the Chandrasekhar mass, leading to the supernova explosion. And the other channel is the single degenerate channel, illustrated in the right panels. In this case, what happens is that the white dwarf is accreting mass from a companion, and this mass accretion leads it to reach the Chandrasekhar mass limit and then explode as a supernova. The estimated galactic supernova 1A rate is of the order of 10 to the -3 per year. Even though this doesn't sound like a huge number, we actually have trouble finding enough progenitors for this scenario, leading to the so-called progenitor problem. From the point of view of the single degenerate channel, what happens is that massive white dwarfs are actually quite rare. You can see that illustrated in this number histogram here to your left, showing white dwarfs within 100 parsec that were observed by this longitudinal sky survey. And you can notice that there's a big drop around 1 solar mass. There's very few stars above this limit. And in fact, most of these massive white dwarfs are attributed to mergers themselves. So they typically don't even have a companion that could donate mass and trigger supernova. The double degenerate channel also doesn't have a lot of progenitors, and even a dedicated survey found only 2 possible systems that qualify. So considering the white dwarf population, their possible contribution to the supernova 1A rate is of the order of 10 to the -5 per year. So it's 2 orders of magnitude less than the observed supernova 1A rate. So you might be wondering, maybe we are looking in the wrong place. And one of the reasons that could be the answer is that massive white dwarfs, they are actually quite faint and challenging to directly detect. And that is because for white dwarfs, mass and radius have an inverse relationship. So more massive white dwarfs, they are actually quite small. This can be seen here in this diagram that is showing white dwarf with a canonical mass of 0.6 compared to the Earth, compared to the massive white dwarf. Here the radii are to scale. And you can see that the massive white dwarf is much smaller. And because it is smaller, that results in a lower luminosity for the same temperature. In this case here, it's a luminosity 1 order of magnitude less than the canonical mass white dwarf, which is already quite faint itself. But because they are more massive and smaller, they actually have very high gravities, which means that if they have a companion, they can cause tidal distortion of the companion. A tidally distorted star will, of course, show us a different surface area as it rotates. So if TESS observes these tidally distorted stars, what it's going to see is light curve variability, because we are seeing the flux vary as the system rotates, like in this real light curve that you see over here. So one way of finding massive white dwarfs with companions is to actually search for these tidally distorted stars, or to search for short period ellipsoidal variables. But if we are not to look at the white dwarf itself, what should we be looking at? What we did was to look at hot subdwarfs, which are one of the ideal supernova progenitor companions for reasons that are going to be clear in a second. So hot subdwarfs, as the name suggests, are hot objects that lie below the main sequence in the HR diagram. They are core helium burning stars. They have lost their outer layers, so they appear smaller and have lower masses, but they also appear hotter since we're essentially looking closer to their cores. They lost their outer layers probably due to binary interaction, and in fact, the majority of hot subdwarfs are found in binaries. And in many cases, they are found in close binaries with white dwarfs as companions. So we have there all the ingredients for a supernova 1A. They are also typically bright enough for TESS. So it means that we can use TESS to find them. And thousands of those were actually proposed by the TESS Astroseismic Science Consortium Working Group 8. So what we did was to look at all these hot subdwarfs observed by TESS using quick look plots, such as this one, that were tailored to finding variable stars and in particular binary stars. So down here, you can actually see the light curve of our supernova progenitor. And you can see in the Lomskargo periodogram that it has a peak at a period of around 0.83 hours, which leads to this phase-folded light curve in the top right panel. But for ellipsoidal variables, due to symmetry, actually the orbital period is typically twice the peak. So that's why I'm also including this phase-folded light curve here. If you have good eyes, which is not my case, you probably already see the differences between these two phase-folded light curves here. But let's zoom in and actually have a proper look at what's going on and how we can identify these supernova 1A progenitors. So the dominant effect in the light curve is the ellipsoidal variability, which is because the hot subdwarf is tidally distorted. But there are more things going on here. For example, you can notice that the minima have different depths, and that is a consequence of gravity darkening. What's happening is that the equator of the hot subdwarf has a larger radius because of the tidal deformation, which means it's cooler and therefore darker. So the depth of the minima are going to depend on whether we are seeing more of the star's equator or more of its bright pole as the system rotates with a certain inclination angle compared to our line of sight. You can also notice that the maxima have different heights, and that is a consequence of the relativistic effect of Doppler boosting. What is happening is that we get a boost when the hot subdwarf is moving towards us, so we detect slightly more light than when it's moving away. Because this is a relativistic effect, the fact that we are seeing this implies that the hot subdwarf probably has a very high radial velocity. And we did some follow-up spectroscopy and found that is indeed the case. So the radial velocity semi-amplitude of the hot subdwarf is of the order of 300 kilometers per second. So if there's any people who work on exoplanets watching, I bet you're quite jealous of this high semi-amplitude that you can basically detect from your back garden. So here I'm showing both the TESS light curve and the radial velocities folded to the same ephemeris. In the top panel, the TESS data is the gray points. The black points is an average every 50 points. And in red, you can see our light curve model taking into account all the effects that I have just mentioned. And now here is the radial velocities also with the model in red. With this modeling, we can estimate the masses of both components. We found that the hot subdwarf has a mass of around 0.63 solar masses, whereas the companion has a mass of around 1 solar mass. We don't see any signs of a solar type star in our spectra, so this cannot be a main sequence star. It is instead one of the elusive massive white dwarfs. Evolutionary models that we calculated specifically for the system show that the mass transfer illustrated here will begin in around 30 million years. The system is losing energy due to gravitational wave emission, so the orbit will shrink, leading to a merger in around 70 million years. And given the combined masses of these two stars, which are well above the Chandrasekhar mass, this will very likely lead to a thermonuclear supernova. So what we can learn about supernova in general from this system. So this is only the third hot subdwarf, white dwarf, supernova 1A progenitor that has been found, but that already makes this kind of system the one with the more progenitors known. And importantly, all of them are within 1 kiloparsec and in the disk. So if we take a volume limited sample of hot subdwarfs and we look at their birth rates, we can actually estimate how much this kind of binary can be contributing to the supernova 1A rate. And doing that, we found that the contribution is of the order of 10 to the minus 5 per year, which is actually quite similar to the white dwarf contribution. So that shows that this channel should not be overlooked. It's actually a very important channel. But we are still 2 orders of magnitude below the galactic supernova rate, or in other words, we are still short of progenitors. Hopefully, the continued TESS mission will help us find more of the systems and perhaps show us that there are more than 3 within 1 kiloparsec, which would mean that our rate over here is an underestimate. So I'll stop here. Thank you very much for your attention, and I'll take any questions that you might have.
Thank you, Ingrid, for a fascinating talk. I have many questions of my own, but I'll take questions from the audience. Chris Helmiak, and I hope I pronounced that correctly, is asking about how did you calculate the mass? Because the RV curve of the orbit gives you a mass ratio. So what extra components went into actually getting the actual mass of both objects?
So we have spectra for the hot subdwarf, and with that, we can derive the mass of the hot subdwarf. So using the Gaia parallax, we can derive the radius for the hot subdwarf, and fitting the spectra, we have the log G. So we have the mass of the hot subdwarf, and with the mass ratio and the mass of the hot subdwarf, we get the mass of the companion. And independently, we can also fit the light curve and get a mass for the companion, because the tidal distortion depends on the mass of the companion. So there are two independent constraints on the mass, and they both agree.
Okay, you saved me another question. Okay, I'm sure there will be many more questions in the Slack channel, so please go to the Stellar Astrophysics channel to answer those questions. And we will, so thank you, Ingrid, and thank you, Trevor. And we will move on to the Splinter session. But Jen, do you want to take over and show a few things?
Yeah, I'm gonna keep everyone here for just a moment and do a couple of quick announcements. Let me do that. Okay. So as Avi just said, we're about to move into our first set of Splinter sessions. There are 5 different Zoom rooms, including this one, which is room 1. These will be spread across. 3 of the sessions are the full 2 hours that we have allocated here. So the ultra short period planets in room 1, machine learning in room 3, and the chaos session in room 4 will take the full time. The other 2 are an hour long, but we have staggered them so that they don't overlap with one another. So for the first hour of the Splinters, the SETI with TESS Splinter will be in room 2. And then in the second hour of the Splinters, the TESS GI Splinter on using light curve will be in room 5. You should be able to find the links for all of these in the logistics email that Avi sent you last week, as well as on the conference website. And then between sessions, we have the second of our 2 off-topic or kind of TESS adjacent talks. This one is going to be a talk with JPL scientist Stephen Levin, and it's going to be focusing on the Juno mission, which launched, I think, 9 years, 364 days ago. So we're 1 day shy of the 10-year anniversary of launch. Juno has been at Jupiter doing science for the last 5 years, and Stephen will give us some highlights about what they've learned about our closest gas giant neighbor, and maybe a little bit about how it could influence what we think about with TESS. And then after the big break in the schedule, we come back this afternoon. The first thing that will kick us off is our second panel. This one will be about young stars and the planets that orbit them, featuring Ruth Angus, Anne-Marie Cody, Jason Curtis, and George Zhu. And that will be moderated by Ben Monte. So we encourage you all to tune in for that. Hopefully another great set of recaps, discussion, and Q&A with the audience, just like we had with the Exoplanet session yesterday. Okay, and that's all I've got. So go forth, hop into your preferred Zoom room for the Splinters, and we will catch you all later today.
One quick clarification following a question from the general Slack channel. The TESS GI light curve 1 hour session will be first in room 5, and then we will have—
No, I did it backwards. I'm sorry.
Yeah, we apologize for that, but follow what's already on the PDF, which you can find on the website, the detailed schedule PDF. So the first 1 hour session in room 5 is for the TESS GI light curve, and then in room 2 we will have SETI with TESS starting an hour from now. Okay, I think with that, we should let Brian take over and start your ultra short period planets session.
Awesome. Well, thanks, Avi, and thanks so much, Jen. We really appreciate it. Those of you in the room here, we're going to begin our ultra short period planets Splinter session. You're of course welcome to attend. So this session is going to be focused on planets that are very close to their star. This is a topic that has been of interest for me for a long time, and I was really keen to hear from other folks about what they're working on, what their thoughts are. I'm going to text out there. There's the schedule for our session in case you didn't see it on the TESS website itself for the conference. I'm going to try to stick to the schedule, although obviously we're starting a little bit late, so I'm going to make sure not to cut people off before their time is up. And with that comment, our very first speaker is Ian Wong. And Ian, I see you've got your slides up already. Are you good to go? Cannot hear you, Ian. If you're speaking. Let me see.
There we go.
Perfect. Now you're unmuted.
All right. Let me start again. All right, everyone hear me, see me? Okay, all right, thank you. And thank you, Brian, for organizing this very special Splinter session focusing on ultra-short giant planets, well, ultra-short planets in general. All right, so as the first speaker in the lineup of ultra-hot Jupiter talks, let me begin with a brief overview of some of the unique features of these extreme planets to motivate our discussion. So ultra-hot Jupiters are the hottest subclass of gas giant exoplanets, with dayside temperatures exceeding 2200 Kelvin. The intense irradiation environment leads to a dayside atmosphere primarily composed of atomic and ionic gases, including metallic elements that have been detected by high-resolution optical spectroscopy.
Ian, I'm sorry to interrupt you. We're seeing your presenter view right now.
Oh, okay.
So if you can hit swap displays, I think that will, at the top.
There we go. Ah, okay.
Yeah, that's better. Thank you.
Okay. Okay. All right. So furthermore, the hydrogen, the irradiation is intense enough so that hydrogen is dissociated, at least partially, on the day side, and this figures very prominently in the global heat circulation of the planet, leading to enhanced day-night recirculation and dampened day-night temperature contrasts. Here in the bottom right, we see another unique feature of these ultra-hot Jupiters. The intense gravitational interaction between the planet and star can lead to measurable tidal orbital decay on timescales of years to decades. Here is the famous case of WASP-12b. So our new system, TOI 2109, was observed during sector 25, and the light curve was extracted from the full frame images and therefore has the standard 30-minute cadence. Here in the bottom, we see the raw Spock SAP light curve, from which the periodic transit signals at roughly 16 hours were initially identified. Close inspection of the out-of-transit photometric modulation shows synchronous variations that are suggestive of a planetary phase curve. All right, so visible wavelength phase curves of planetary systems contain contributions from several different physical processes. Over the course of its orbit, the observed brightness of the planet varies as a consequence of the changing viewing geometry, resulting in the so-called atmospheric brightness modulation. In transiting systems, when the planet passes behind the star, that is known as secondary eclipse, and the depth of that is equivalent to the relative total dayside brightness of the planet. In addition, gravitational interactions produce also additional phase curve modulations, including ellipsoidal distortion at the first harmonic of the orbital phase due to the tidal bulge raised by the planet on the star. Moreover, there's the Doppler boosting, which results from the Doppler shifting of the star's spectrum, and that is proceeding in tandem with the radial velocity signal. And I'll refer you to my poster, 3.13, which provides a summary of our extensive systematic work on phase curves from test data. All right, so here on the left, we see the systematics removed, phased, folded, and binned light curve for TOI 2109. You see the very deep transits, as well as a very prominent secondary eclipse of roughly 730 ppm. In the middle panel, we see a zoomed in view of the phase modulation. We have strong detections of the atmospheric brightness modulation in the solid blue line and the ellipsoidal distortion in the dashed line. The night side flux in the test band is consistent with 0. So in addition to the synchronous modulations, we also find some additional periodicities in the light curve. In the bottom right, we find the Loam-Squargle periodogram with the best fit phase curve removed. And we find these two large peaks at roughly 0.61 and 0.97 days. The x-axis here is frequency normalized to the orbital frequency. In addition, we find a first harmonic modulation at the 0.61 day period, which is the third peak there. All right, so having this unique detection reported, we embarked on a very intensive follow-up effort, obtaining 17 full and 3 partial transits with a variety of ground-based instruments. Particularly notable is the 3 high signal-to-noise multi-band Muscat visits. And here, those are shown in the panels on the right. Those exquisite photometric series enabled dramatic improvements to the transit shape parameters as well as the orbital ephemeris over the 1-year baseline of our observations. The transits are achromatic, which is the first evidence against false positive scenarios. In addition, we were able to obtain a KS band secondary eclipse with the Palomar work instrument that is shown in the small inset figure and has a depth of roughly 2,000 ppm. For RVs, we relied on 2 instruments, TESS and PHEIS, for a total of 30 individual RV measurements. From those spectra, we were able to detect significant rotational broadening and retrieved a rotational velocity of roughly 82 kilometers per second. And this fast stellar rotation contributed to the large error bars you see on the left for the RVs. Nevertheless, we were able to obtain very good coverage of both quadratures as well as near the transits, and we were able to retrieve roughly 6 to 7 sigma signal due to the planet, the reflex motion of the star. In addition to these individual visits, we also went out of the way to get 2 spectroscopic transits with TESS. And here in the bottom right, we see a very faint Doppler shadow signal in the line broadening profiles. And once we folded in the orbital constraints from the photometric light curve fits, we were able to get a very, very tight constraint on the sky projected obliquity that is very close to 0. So to summarize, here are the results, and note that this figure is drawn to scale. And the host star is a mid-late F star, roughly 6,500 Kelvin, and roughly solar metallicity. It has a mass of 1.4 solar masses and a radius of 1.7 solar radii. The age is pretty poorly constrained. It's roughly 1.5 gigayears, and it lies at a distance of 262 parsecs. Here we see, once again, the rapid stellar rotational velocity. The semi-major axis is less than 0.02 AU, which enables me to fit this on very nicely on this scaled plot. For the planet, we measure a orbital period of 0.67 days to less than 1 millisecond accuracy. And by virtue of the immense volume of ground-based photometry, we were able to get very, very good constraints on the orbital geometry, with constraints on the inclination of 61 degrees with an error of 0.3 degrees. From the Doppler tomographic transits, we were able to get a sky projected obliquity lambda of 1.8 plus or minus 1.6 degrees. So this is suggesting a very well-aligned system. The RVs indicate a mass of roughly 5.1 Jupiter masses, and the planetary radius is about 1.3 Jupiter radii. Since we have both a TESS and a KS band secondary eclipse, we were able to fit a black body through those secondary eclipse depths, and it fits very well, and we get a day side temperature of 3633 Kelvin. Meanwhile, since the night side flux is consistent with 0, we are only able to place broad constraints on the night side temperature, which are 2500 Kelvin at 2 sigma. So let's place TOI 2109 in context. This planet, as suggested by the title, has the shortest orbital period of known gas giants. Here on the left, I show the mass radius diagram of gas giants, where we can appreciate that TOI 2109b is among the most massive exoplanets discovered to date. Meanwhile, on the right, we have the planets ordered by insolation flux on the day side. And 2109b has the second highest irradiation level on the day side, and also the second highest day side temperature. And this is behind the extreme end member Kelt 9b, which is at the very top right corner. We notice that this covariance among the bulk of the gas giants is the well-known radius irradiation relationship, indicating irradiative inflation. Meanwhile, 2109b is significantly offset from this core correlation by virtue of its high surface gravity. Okay, so moving on. So let's look to the future. So what can we do with this very, very remarkable system? So by virtue of its the moderately bright host star, as well as its extremely close orbital separation, TOI 2109b is an exceptionally attractive target for intensive atmospheric characterization, particularly in emission. So here in the top left, we have the ESM, the emission spectroscopy metric, and we find that TOI 2109b has the 5th highest of known gas giants. So on the right are results from our forward modeling of the day side and night side emission spectra. And we see that day side is predicted to be largely featureless, except for this kind of low bait feature, short word of 1.7 microns, which is the telltale sign of hydrogen dissociation. These models are parameterized with the day-night heat recirculation parameter epsilon. And we find that there is a moderately efficient day-night heat recirculation in line with predictions from GCM modeling of ultra-hot Jupiters. Meanwhile, on the night side, we don't have very good constraints on the night side temperature, as I mentioned before. So infrared observations are needed to really pin down the day-night heat recirculation and the day-night temperature contrast. But suffice to say that we expect very deep near-infrared absorption features due to H2O and carbon monoxide. And these are, this makes it extremely accessible to current and near future facilities like J2ST and HST. So in the interest of time, I'm going to skip one slide and just go to my final slide, which is showing the predicted orbital decay rate of gas giants. So as I mentioned in the introduction, we have one incontrovertible detection of orbital decay from WASP-12b. But we find that if you assume a common tidal quality factor for the star, TOI 2109 has the fastest predicted orbital decay rate. And this will be extremely prime fodder for follow-up observations. And TESS itself will return to the target in Sector 52, which will take place in mid-2022. At that point, we will have more than 2 years of time baseline, which should be sufficient to retrieve orbital decay rates at the upper end of the predicted range.
Okay, Ian, I'm going to go ahead and cut you off there. That is so fascinating and very exciting. You have some questions already in the Slack, and I'm going to encourage folks to post your questions over there and let us move on to the next speaker. Thanks so much, Ian. That was awesome. Okay, our next speaker is Brett Addison, and we're going to hear about another ultra-hot Jupiter. Brett, are you able to load up your screen?
Yep. Can you hear me all right?
Yes, can hear you.
Can you see my slides?
There we go. Perfect.
All right. Awesome. Thank you again for organizing this Splinter session. So my name is Brett Addison, and I'm a research fellow at the University of Southern Queensland. And today I'll be talking about the discovery of TOI 1431 and Mascara 5b, which is an ultra-hot Jupiter orbiting one of the hottest and brightest known exoplanet host stars. Okay, so you might be wondering, well, why is this planet also called Mascara 5b? And that's because it was first detected by the multi-site all-sky camera, also known as Mascara. So here I'm showing the phase-folded photometry, showing the transit, as well as the periodogram here that indicates that the planet's orbit is approximately 2.65 days. And this was observed between February 2015 and March 2018. And then after Mascara detected the transits, TESS observed this target and detected transits in sectors 15 and 16 between August 15th and the 7th of October 2019. So here I'm just showing the simple aperture photometry for both of those sectors, and you can clearly see the deep transits in the photometry. And I also indicate the momentum dumps here, where I split the light curve into segments for the global fit that I did. And here I'm showing the PDC version of the light curve with the split segments, and you can see a nice deep clean transit with a period of 2.65 days, same as Mascara. So in the title of my talk, I said that this is one of the brightest and hottest host stars. And you can see that the V magnitude of the star is approximately 8, so it's extremely bright. I did a SED fit using ExoFast to derive the stellar parameters, including the effective temperature, which is nearly 7,700 Kelvin. So this star is extremely hot. I also derived the spectroscopic properties from the Song spectra, SOFI, and Theus. And you see some disagreement, but the important thing that I want to highlight here is the very slow rotation of the star with the V sign on between 6 and 10 kilometers a second. And this is a bit surprising because this is an A-type star that's extremely hot. You would expect a very fast rotation, but this is actually classified as an AM star, which is a chemically peculiar star. And these types of stars typically are found in a binary where you have a very close stellar companion that spins down the star due to tidal tides raised on the host star. And here I'm just showing the effective temperature of TOI 1431 in relationship to other planet hosting stars, and this is in the top 10 hottest stars to host a planet. So to confirm this planet and measure its mass, we obtained radial velocities from several instruments. I led the effort to obtain radial velocities on the Song telescope in the Canary Islands. And as you can see from the radial velocity fit, I get a semi amplitude of 294 plus or minus 1.1 meters per second, which is extremely precise orbit for a star this hot. In fact, I would say this is probably one of the most beautiful radial velocity orbits you've ever seen for a star this hot. And from the joint fit of the TESS light curve, all the ground-based light curves, and the radial velocities that you see here, I was able to measure the mass and radius of the planet. So the mass is a little over 3 Jupiter masses, and the radius is about 1.5 Jupiter radii. And of course, I mentioned there were ground-based follow-up, transit follow-up of this. And I would really like to thank the SG1 community for doing the follow-up of all of these TOIs, because not only do they help confirm these planet candidates, but also help to improve the precision on the orbital period and the transit midtimes and keep the ephemerides up to date. So the most exciting thing about this planet is being able to measure the thermal emission from this planet, because it orbits a star that's super hot and it's a very close orbit. And using the TESS photometry, we were able to measure the day side and night side emissions. So here I'm showing the phase curve, which also includes the occultation. And from modeling the phase curve using these phase curve parameters, we were able to determine the day and night side temperature of the planet. So the day side temperature is about 3,000 Kelvin, so extremely hot, and the night side temperature is close to 2,600 Kelvin, making this is actually the second hottest night side temperature ever measured. And from this, we were able to also calculate the heat recirculation efficiency from the day to the night side, which is quite high. It's one of the highest ever measured. And we also measured the bond albedo, which is quite negative. And the negative bond albedo basically tells us that the thermal emission from the planet cannot be accounted for by the energy input from the stellar insolation alone. So now let me just quickly compare this planet with other hot and ultra hot Jupiters that have their day and night side temperatures measured. So here I'm plotting the night side temperature with the equilibrium temperature, and TOI 1431 is pretty similar in terms of its nighttime temperature to HAT P7b, just slightly hotter, making it the second hottest ever measured. And then of course you have Kelt 9b, which is the hottest planet ever discovered. Here I'm showing the bond albedo, and again, it's quite similar to HAT P7b. Both planets have a very negative bond albedo. And then here I'm showing the recirculation efficiency. And again, these two planets are very similar with a very high recirculation efficiency. Now the planet radius for this planet is a bit inflated. And here I'm showing the planet mass and the planet radius, and you can see that the radius is a bit inflated compared to similar planets of similar mass. And what this is telling us, so if we look at the radius evolution for this planet using different models of irradiation and deposited heating in the interior, we can see what the radius evolution what the radius of the planet will be over time. So the models that best fit the radius of this planet are the ones with irradiation and irradiation plus a little bit of heat deposited in the interior. And this only works if the planet either formed in situ or after 1 or 2 million years after formation, it migrated very quickly into its current orbit. Otherwise, the no heating model would suggest that the planet radius should be significantly less. Now, I also mentioned that this is an AM star, and AM stars typically have short period stellar companions. So far, we only know of about 5 transiting planets around AM stars. And one of the questions that I would like to throw out there and propose is, can these short period Jovian planets spin down their A-type host and as such transform them into these chemically peculiar stars? And if the answer to that question is yes, then I propose that we actually search for planets around these stars using radial velocities and transits for AM stars that don't contain a stellar evidence for a stellar companion. And because I'm running low on time, I will conclude here. One thing I want to mention is that earlier I said that the radius is inflated because the planet likely migrated very quickly to its short period orbit, and we actually have evidence of high eccentricity migration from from the Roster-McLaughlin effect that Stangert et al. 2021 measured the RM for this planet and found that the planet is in a retrograde orbit. And with that, because I'm out of time, I will end there.
Wow, that's just fascinating. What an interesting system. I'm going to encourage folks to ask questions on the Slack here, just so we can stay on schedule. But yeah, just really fascinating system. And next up, we have Jake Turner. Oh, excuse me, Nicholas Saunders, who's going to tell us a little bit about hottest Jupiters around evolved stars. Let's see. And Nicholas, are you able to bring up your presentation?
Yeah, I'm just sharing my screen now. All right, let me know if there's any issues with my my presentation, but I'll go ahead and dive in. Start by saying just thanks so much for organizing this session. There's a really interesting spread of planets to be discussed here, so I'm really excited to see some of the results. Yeah, I'm really glad to be included to talk about some of the stuff that we've been working on, which is specifically targeting planets orbiting evolved stars using TESS in the FFIs. And so you might have seen my talk advertised during Sam Grunblatt's talk yesterday, or on Twitter with this sensationalized version of what I'm going to be talking about. But I'm going to be diving into a little bit more detail today. But if this is why you're here, I'm glad that the clickbait worked. So specifically, I'm going to be diving into some of the stuff that we've been working on for planets orbiting evolved stars, and to start just by motivating why we're interested in studying planets orbiting evolved stars. There's a few questions that you can answer with this type of system. And so some of the really key things that are still unknown about the late evolutionary stages of a planet's life are: how do planets become reinflated at late times? What's the source of some of the anomalously large radii for hot Jupiters that we see? And does this persist for evolved stars? How does planet engulfment operate on timescales for evolution for stars? Does the increased radius of stars dramatically affect the tidal interactions and cause engulfment to happen on faster timescales? And at which distances can planets survive? And finally, how does planet occurrence change as a respect of some of the stellar properties that we can observe, such as stellar mass, composition, and of course, evolutionary state? And so I'm going to be talking about some of the systems that we've discovered so far. We have 4 confirmed systems that we're currently working on publishing, and a handful of others that are exciting. But this is kind of what the picture looked like before TESS. There was a very, very small sample of stars of evolved stars with confirmed exoplanets orbiting them. And these 2 regimes that I've highlighted are really important for answering some of those questions. So this teal hatched area is the regime where we expect planet inflation to occur based on the incident flux you receive and the planet radius. And then the kind of tan region on the left is the migration regime, where the tidal interactions are strong enough where we expect measurable tidal decay over the time scale of a star's post-main sequence lifetime. And so this is what the picture looks like after a couple of years of TESS. So the gray points are confirmed published TOIs. The red points are some of the evolved CTOIs, the community targets of interest. And then all of the red points are things that we've discovered in our survey. And the larger red stars are the 4 that I'm going to be discussing today. You can see they span kind of a range of parameters, but all fall within both of these regimes of interest to our study. And so this is where the host stars fall on an HR diagram. You can see there's some of the more evolved systems that have been confirmed by TESS. Each of the points on this is a confirmed TESS planet host. And so we're actually starting to probe some of the stars that are evolving up onto the red giant branch and leaving the main sequence and increasing in radius in a significant way. And so the first system that I'm going to talk about is TOI 2184b. This is the first planet that we discovered in our survey. You can see here the folded TESS light curve on the left, and some of the radial velocity measurements that we've received for it on the right. So this is a southern hemisphere target. It's in the southern continuous viewing zone. And so we received radial velocities from these 3 instruments you can see here. And one of the really exciting characteristics of this system is that based on its mass and the amount of incident flux it receives, it appears to be non-inflated. So it's orbiting this subgiant, a fairly massive early subgiant. But despite the high incident flux that it receives, you can see on the x-axis, its radius is smaller than we'd expect based on its mass, using kind of theoretical predictions for the radius you'd expect given these parameters. And what I've shown here is this pink dashed line is kind of its expected evolution in incident flux since its 0-age main sequence. You can see that it's maintained this high level of inflation, but it's definitely something of an outlier in terms of its inflation level at this stage. And so it's an interesting data point for understanding at which stages radius inflation may occur, and whether it's an effect of the increased irradiance you get, or if there's some kind of tidal interaction that's dumping heat into the interiors of these planets to inflate them that way. So the next planet that I want to talk about is TY 2337b. This is the next planet that we discovered, and it's an incredibly short period hot Jupiter orbiting a red giant branch star. So you can see it as a sub 3-day period around a star that's greater than 3 solar radii. And so what we can see here is the radius of the star on the x-axis versus the semi-major axis on the y-axis. And you can see that it's one of the closest planets to the surface of its host star, essentially in terms of the A/R star value. And so this is a planet that may be within the regime where tidal interaction could be causing measurable orbital decay, and this is one that we'll definitely want to follow up in the future as the TESS extended mission revisits the system. And it's an exciting idea for measuring some of those effects later on. So the next one is a brighter target that has these very deep transits that you can see on the left. It's a slightly larger star. It's a highly inflated 1.6 Jupiter radius planet. And it's also on an incredibly short period, a sub 3-day period. And this is likely the best candidate that we have so far for atmospheric characterization with missions like TESS, with missions like James Webb in the future. The brightness of the host combined with the depth of the transit and the level of inflation of the atmosphere mean that there's likely a high level of transmission spectroscopy that could be measurable in the future. We have the simulated James Webb spectrum on the bottom here. And so there's exciting opportunities for actually measuring some of these spectroscopic transit effects for a system like this. It's this is definitely going to be an exciting system to follow up in the future with other missions and potentially target that with something like James Webb. And so the last one that I want to talk about today is TY 2669b. This is another highly inflated hot Jupiter orbiting red giant branch star. And you can see this incident flux planet radius diagram on the left shows some of the radii of the last 3 planets that I've talked about. And they span a very wide range of inflation level. As you can see, this familiar trend that we've seen a few times today for inflation as a function of incident flux. And you can see that this one is very inflated relative to the other ones that we've seen, but it's also around an incredibly evolved star. So you can see this green point here is the HR diagram position of its host star. So it's starting to ascend the red giant branch. That's about 4 Jupiter radii for 4 solar radii for the radius of the host star. And so it's one of the most evolved systems that we've seen so far. And it actually has a tentative astroseismic detection, which we're following up. We only have a couple sectors of data for it so far. And so looking to the future, we'll have more data, a longer baseline. We'll be able to potentially probe the interior physics of the star and get a better sense for the stellar parameters using astroseismology, which is another potential application of TESS, especially with future shorter cadence full frame images. So just to summarize here, the 4 planets that we talked about today, these are representative of some of the things that we're trying to learn through our survey of planets around evolved stars. There's lots of exciting candidates that we've discovered as well that we're looking forward to following up in more detail. But if you're interested in learning more about these, we have 2 papers that are in prep right now that should be submitted very soon. And so if the BuzzFeed wasn't quite highbrow enough for you, here's a maybe slightly more refined teaser for the fact that we're going to have some papers out before too long. The first paper should be out by hopefully the end of the conference. And so with that, I'll just put this figure up again to just emphasize again that these are some of the questions that we're interested in answering for the late evolution of planetary systems. And I'm happy to take any questions that you have.
That was great, Nick. Thanks so much. Yeah, some questions here on the Slack. I see Elizabeth Adams is asking. Oh, Elizabeth, why don't you just ask your question because you're on the panelists.
Sure. I was just wondering for TY2337, the RGB planet that's under a 3-day orbit, if you had an estimate for how fast its orbit would be decaying, like when can we see that orbital decay?
So we've tried creating a model for it. There was some. Let me pull up. Yeah, so 237. Yeah, so we tried to fit a model to the orbital decay using just the TESS data that we had with a baseline of about 2 years, right, with a few sectors. It was probably too short for our predicted decay. I mean, we expect orders of minutes, maybe to tens of minutes for like the amplitude of decay over that time scale, and we just don't have the precision to do that. We also followed it up from the ground more recently, but it's yeah, still slightly inconclusive for the orbital decay model. It's going to take a longer baseline, we think. But yeah, so following up in the extended mission with higher cadence, we'll be able to get a more precise estimate of the transit timing. So hopefully that'll help out there.
And I see you have a question on the Slack from Alexander, who I believe is one of our panelists here. So Alexander, you want to ask your question?
Sure. Can you hear me?
Yep.
Thank you for the great talk. I was just wondering, these 4 systems that you were discussing, mentioning, and that are about to be published, is there any indication that any of them have distant, stellar, or massive planetary companions?
We've searched the RVs for any outer companions. There's no indication that there are outer stellar companions. We think that those would be measurable in the RVs. And
I'm thinking more
also,
like the scale of like hundreds of AU, like even like visual binaries.
Yeah, so we've cross-checked these with Gaia, and there's no resolved binaries in our sample.
Gotcha. Thanks.
Thanks for that, Nick. And can I encourage you, Nick, also to answer those questions on the Slack for folks who are not able to attend here in the Zoom?
Definitely.
Perfect. Okay, next up, Jake Turner is going to tell us about decaying orbits of WASP-12 and WASP-4 as seen by TESS.
Okay. Can you see my slides?
Yep, you're looking good.
Okay, so I'm good to go. All right, well, thank you everybody for coming. Yeah, as Brian said, I'm going to be talking about 2 hot Jupiter systems, WASP-12b and WASP-4. So I'll just jump right in. So what we're trying to do is look at the orbital decay of these planets. And so if on the left, you can see, let me see if I can, yeah, you can see this nice period radius diagram. A lot of people have been showing this already throughout the conference, showing some of these, short, the hot Jupiters, the ultra short planets, hot small planets. So there's a lot of planets that are, really short orbital periods, less than 10 days. And we believe that orbital decay is going to play a role here. Theoretically, there's been a lot of papers over the decades about this. And so for close-in planets that are orbiting stars with surface convective zones, we believe that this orbital decay might happen. Basically, there's going to be a tidal interaction between the host star and the planet, and the host star will spin faster and the planet's orbit will decay. So there's some interaction there. And there's this like nice figure from this paper by Matthias. So that's kind of what we're looking for. Again, this is mostly theoretical, so we're trying to actually get some observations to constrain these models. So the 2 targets that we're looking at is WASP-12b. So WASP-12b is, it's it orbits in about 1.09 days, so it's really zipping around. And we know it has an escaping atmosphere from Hubble observations. There also has been, it has a decaying orbit from all ground-based observations. So I'm showing a figure here versus Epoch has been observed for, many, about a decade now or a little bit longer. And so you can start seeing that there's some variation in the transit timing variations, basically. So you can start seeing that the stuff is happening in this, that they're comparing it to orbital decay, but also precession here in this paper. So we're trying to follow, these are all ground-based observations. So we're trying to follow this up with TESS. And then WASP-4b is another typical hot Jupiter. It orbits about 1.33 days. And there also are some signs of a changing orbit. So this is showing, and some of the results from Bluhm et al. 2019, which is actually was the first sector 2 of TESS. And they compared this to all the other ground. So this is the stars, the TESS data, and they're comparing this to the other ground-based observations, and they show there were some signs of a possibly changing orbit. And so they're trying to figure out what was causing it. And so we're going to follow that up with basically all the sectors of TESS that have been observed so far with WASP-4b. So basically jumping into our results, so we can show here the WASP-12b data from TESS. So you can see time versus flux. You can see the transits really, really well. We also are able to resolve the secondary eclipse. So if we bin all the data together, we can see that there is a secondary eclipse here. So that's what I'm showing here. So we can't see each individual secondary eclipse, but we can see them all averaged together, which is really nice. And so when we compare this to the previous observations, this is what I hear for epoch versus basically the transit timing variation. So you can see these are all the ground-based observations, and this is the TESS observations that we derived for the transits. And you can see that it fits the orbital decay model a lot better than the precession model, statistically significant. And the same with the occultation. So there's been some occultations from the ground, and our occultation from TESS is quite good. And this is also consistent with orbital decay. So there's definitely orbital decay going on in this planet, both from ground-based and TESS observations, which is really interesting. And so using those results from our observations, we can get some parameters of the system itself. So we get about 32 milliseconds per year is the orbital decay. So it's quite a small change, but we can actually measure it, which is really, really interesting. And so if you put that into how long will the system be around for, it'll be around for about 3 million years. And so if you put that into perspective for the atmospheric escape, because we know the atmospheric escape timescale is about 300 million years. So the planet's going to basically be inside of its star before all of its atmosphere is stripped away. So it's kind of interesting. And so using the orbital decay rate we derived using this equation, we can actually get an estimate on the modified tidal quality factor of the star, and we get about 1.4 times 10 to the 5. And so that's interesting because it is consistent with the lower end of some predictions. So I'm kind of showing here some predictions by Barker 2020 with different ages of stars by the Q factor, and you can see they kind of range all over. But some of this observation is consistent with some of these other predictions are a lot higher. There's also been some uncertainty of what stage of WASP-12b is at, if it is on the main sequence or if it's evolved. And so whether it should be undergoing orbital decay based off the orbital decay model. And so there's actually some more work to be done in order to understand why this system might be undergoing orbital decay if we're not sure when, what we got to be. Basically, I've got to figure out what stage its life is at to understand its orbital decay. But we definitely know its orbit is changing, which is interesting. So going into some more of the WASP-4b. So as I said, there was some signs of a changing orbit, but there was a recent paper by Bluhm et al. 2020 that showed that the changing orbit might be due to the planet accelerating towards Earth. So I show here some of their results. This is looking at the RV measurements. So phase versus RV, and you can see that they found this slope with some new RV measurements. But again, there's a lot of time that's between the old measurements and the new ones. So there's some uncertainty there, but they did find that there was a linear acceleration towards Earth, and that could explain basically the changing orbit. So it wouldn't be a decaying orbit. Basically, the planet just on a normal orbit, but the whole system is accelerating towards us. But we did our own RV analysis. There's been a bunch of other RV measurements that have been presented in the literature. So we included all of that in our analysis, and that's what I show here on the right. And so we actually see that there is no linear acceleration, so that we don't think that's the cause of the changing orbit. So jumping to some of the TESS observations. So yeah, as I said, the first sector of TESS was observed and published, and that's what was the first indication that there was a change in orbit of WASP-4b. And so we analyzed all 3 sectors. And this is showing all three sectors, bend together. Unfortunately, we don't see a secondary eclipse, so we only have an upper limit on that, so we can't actually use that for the timing. But we do actually confirm with all three sectors of test data, including all the ground-based data, that there is a change in orbit. Unfortunately, this is not as well as constrained as WASP 12b, so it can actually be orbital decay or a precession. Both models are preferred, so we actually need more observations in order to tell the difference between the two. And so we did some predictions of when you might be able to tell like a difference between the two models. And so again, this goes all the way to 2030. And so hopefully by the mid 2020s, 2025, I'm showing here some of our predictions and just randomly choosing some of our MCMC results. So, you can see that the models are definitely converging. And so we're hoped by mid 2020s, we can actually tell the difference between the two models of whether it's orbital decay or a precession of the planet itself. And so, yeah, we definitely need more observations from the ground, and if a future extension of TESS observe this. Right now, I don't think there is. It's supposed to be observed again by TESS, but maybe if it's extended in the future, maybe it will be. So yeah, we're really unsure about what's going on with WASP 4b, but it is definitely an interesting system. So basically going into my conclusions. So yeah, I didn't mention this, but TESS has been really well characterized for searching for TTVs. There's been a lot of studies like characterizing how well the timing is on TESS, and it's like really, really good. So, we were very confident that TESS is really good for studying orbital decay of planets. So yeah, as I mentioned for WASP 12b, we confirmed the orbital decay that was seen from the ground. So we confirmed that with both the transit observations and occultation from TESS, and we get some of these physical parameters out of that. And then for WASP 12b, we also confirm with all three sectors of TESS that it has a change in orbit. There is a slight preference that this is orbital decay, but however, it's not certain. So we need more observations, but we do show that the system is not accelerating towards Earth. So there definitely something is going on with the planet that's very interesting. So we stay tuned for more observations. So thank you. That's all I got.
Fascinating, Jake. That was really great. Some really good questions on the Slack here. Let's see. We've got. Forgive me, Melinda. I'm not sure I can pronounce your last name correctly. Melinda Suarez Furtado. She asks, is it possible to detect signatures of mass transfer in systems undergoing orbital decay? Do you see any indications of that for these systems? Well, WASP 4, I guess, but WASP 4, anything there?
That's a great question. We haven't actually looked into that, so that's an interesting question. I haven't really looked into that, but I definitely think I'll take a look. So I don't actually have an answer to that, but that is a very good question. It's definitely something to look into.
And another question, Sam Quinn asks, did you try fitting a quadratic trend to the RV as for WASP 4? The residuals seem to show hint of variation.
So we did try to fit it with a quadratic trend, and it doesn't really fit. We did try to fit it with the multiple planets, and there was some indication there could be another planet there, but it was very uncertain. So right now we're not quite sure what is going on with the residuals of the WASP 4 RV data. But yeah, it definitely doesn't fit really quadratic, and so we're still looking into that. But yeah, we did try to fit it with a few different models, and none of them are really preferred over just the standard non-acceleration model. So yeah, that's a good question. So again, we also need more RVs, because then we can tell if there's any more periodicity or structure in the future RVs as well. So.
Perfect. And Elizabeth, why don't you go ahead and ask your question?
Yeah, sorry. If I just was curious how WASP 4's decay rate compared to WASP 12.
Yeah, so I think we get, I think I got a backup slide showing all the values that we got for WASP 4. Where did yeah, I know that's what, I guess I didn't. Okay, so I think it was about 7. Yeah, there we go. So assuming that it's due to orbital decay, we get about 7 milliseconds per year. So it definitely is smaller, and that's to be expected because the signal is definitely smaller in the TTVs. Yeah, and so we get an orbital decay timescale of 15 mega years. And so if we actually calculate the modified tidal quality, we get something that's basically an order of magnitude below all predictions. So we're, if that is true, if that is true, it's uncertain what is really causing that. So that will definitely be a very big, interesting theory problem for people to solve. So again, this is assuming it's orbital decay, which we don't conclusively know yet. So just keep that in mind. But if it is, it's going to be very interesting. There's going to be something we have to figure out.
Great.
Cool, thanks. Excellent.
Jake, and let me encourage you to answer the same questions in Slack as well.
Okay, sounds good.
Let me switch now to Alex Hindle, who's going to tell us about the effects of magnetic fields in the atmospheres of ultra-hot Jupiters.
Oh, I need to stop.
Let me just share my screen. Cool, is that all good? Yeah, great. So thanks, Brian, and thanks for everyone involved in organising this session. It's been interesting so far. So for those who don't know me, I'm Alex Hindle. I'm a postdoc at Newcastle University in the UK, and I'm working with Tammy Rogers and Paul Bushby until February 2023. I'm going today to present some work that I carried out during my PhD with the same team. It's resulted in 2 recently accepted publications down here, so check them out if you're interested in anything here. So first, let's go over the problem. So until recently, phase curve measurements of hot Jupiters have universally found eastward hotspot offsets. And this is well explained by hydrodynamic theory, which always predicts this. So it always predicts eastward hotspots and eastward winds. So as an illustration here of a hydrodynamic solution with an eastward hotspot. But to date, there have been 5 exceptions from this. HAPI 7b, CLAP 76b, CORO 2b, WAS 12b, and WAS 33b. 4 of these ultra-hot Jupiters, with CORO 2b being an exemption, it's much cooler. And there are 3 general explanations that have been proposed for this. Cloud asymmetries confounding observations, but recently, ultra-hot. It's been proposed that ultra-hot Jupiters, the day sides are hot enough that, on some of them at least, that the clouds will be vaporized, and this shouldn't be necessarily be an issue on some of them at least. Asynchronous rotation would explain such observations, but due to, well, these planets, especially the ultra hot ones, but all of them actually, they're on highly circular orbits with near zero eccentricities, so they're expected to be tightly locked. And finally, magnetism. Hotspot oscillations have been produced by 3D MHD simulations, but the mechanism driving them was, until now, not well understood. So our goal was to develop an understanding of the magnetic mechanism that can trigger the reversals using a reduced physics shallow water MHD model. And I've got some a schematic and some simulations down below, but I won't really have time to go into the model in that much detail because obviously it's a pretty short talk. So before we go into any mechanisms, let's go into some, just look at the magnetic field geometry on hot Jupiters, because I'm sure a lot of people here are magnetism experts or MHD experts. So 3D MHD simulations generally found that hot Jupiters have equatorial antisymmetric toroidal fields that dominate in the hottest hot Jupiters. As you can see in the bottom 2 panels here, so they've got these equatorial antisymmetric strong toroidal fields. Why is this? Well, hydrodynamic theory predicts strong zonal flows wrapping around the planets. But these hot Jupiter atmospheres, if they're hot enough, they're also partially ionized. Hence, as these flows pass through a deep-seated magnetic field, an atmospheric toroidal field gets wound up. So the magnitude of this toroidal field scales proportionally with the planet's deep-seated field and the conductivity. And that's highly temperature dependent. So in cooler planets, the toroidal field is weak, so the magnetic solutions behave similar to the hydrodynamic counterparts, whereas in hotter planets, the toroidal field can be strong and complex magnetic behaviors can start to emerge. So in this bottom row, we've got some really interesting time-dependent magnetic behaviors emerging. So right now, let's go at some of our findings. What triggers the hotspot reversals? So first, let's start with the hydrodynamic case. So in hydrodynamics, it's well known, Schopenhauer showed that drag-adjusted geostrophic circulations cause eastward hotspots. And what they do is they transport thermal energy from the western equator up to higher latitudes and then back down to the western equator by sort of circulation. And this drives the eastward, this drives a hotspot eastward. This also, these flows are also momentum transporting and they cause equatorial superrotation. What a strong toroidal field does, it obstructs these circulations. It causes, so if we put a field in, these circulations will attempt to flow and they'll carry the magnetic field with it and it will cause a kink. And this kink does two things. It tries to prevent and block these circulations in the meridional direction, north-south. In the zonal direction, the geometry of the kink always induces a westward acceleration. So what this does is it means that the flows get confined into the equatorial regions, and also a westward acceleration drives hotspots westward. For more details of this, I've got a poster up, so come see me at a talk and I'll go through it. Come talk to me at a poster, I'll come explain it in all the gory details, or you can check out our poster. So once we understood the mechanism, what we did is we came up with some simple power scaling laws, based on the mechanism. And these fit relatively well with what we find in our simulations, especially in the regions that or parameter space that are appropriate. So what this VA crit is, it's an Alfvén speed for the toroidal field strength. So we have a criticality condition in terms of the toroidal field strength, but what people are really after is the dipole field strength, planetary magnetic field strength. So we relate this by this previously mentioned scaling law, where the toroidal field is proportional to this thing Rm times the dipole field strength, where Rm is related to the conductivity of the planet. So we then want to apply this to actual data. So we look at the Exoplanet.eu dataset and apply our results to that. And here we've got a B-dip crit, so our critical dipole field strength plotted against temperature of equilibrium temperature of these planets. And as you can see, the requirement of the dipole field strength needed to cause reversals or wind variations drops off quite significantly as temperature increases. So in the cooler, we've split into three categories: cool hot Jupiters, where you need implausibly large magnetic fields to explain westward hotspots. So here we conclude that CORY2b's observations are probably not from magnetic origin, because we'd need kilogauss magnetic fields to explain that. Whereas conversely, for the ultra hot Jupiters, we've got very weak to moderate magnetic field strength requirements needed. So these two lines, so the lower dashed line is compared to just Jupiter, so that's 14 Gauss, and the dotted line is twice that. So all of these can be explained by feasible magnetic field strengths. And what that means is that if you're trying to model these planets, or these ultra hot Jupiters, you should really start considering putting an MHD into your model, which is always not always easy. So people often put a linear drag in, but this is actually not that good a thing to do, because now we're moving beyond the regime where that should actually be done. There's an intermediate range 2, which is perhaps most interesting. That can, in future, as we fill this kind of diagram out, it can indicate typical magnetic field strengths in hot Jupiter atmospheres, which at the moment we've got no real idea of. So that's quite exciting if we can start filling this out. So as a result of this, we've been trying to attempt to guide some future research, partially with TESS. So the foreknowledge of the hot Jupiters that we've identified magnetism should be important in has allowed ourselves with Brian and Elizabeth to combine. So we've set out a project proposal where we want to combine some phase curve measurements with bespoke 3D modeling. See Brian Jackson's post for some more details on everything to do with that project. But here is just a table of some of the planets we're looking at. And as you see, we're looking at some with a range of requirements, so a range of temperatures and a range of magnetic field strengths required. There's also one more that I've not put in this table because it wasn't in the data set that I did as I quickly prepared for this meeting. One thing to note, you can do this yourselves. HAT P7b and Kepler 76b's observed brightest spot oscillations are on timescales of 10 to 100 days. So obviously for TESS, which generally is somewhere in that window, but not at the large end of this window, it could be possible that you actually miss a westward observation. And this is a plug for our recent paper. We've highlighted 65 hot Jupiters of interest in that, and I'm currently planning on putting a huge list of all the hot Jupiters up somewhere, probably on my website, but I have not done yet because things get in the way, don't they? Okay, that's all. Thanks very much.
Brilliant, just fascinating. Let's see. One of our questions in here. Yeah, do you want to say something, Alex, about what kind of constraints, like what kind of precisions can we get on magnetic field strengths by looking at these phase curves? Are we going to get to within factors of 2, factors of 10?
That's a good question. So, right, actually, I should probably go back into full screen mode. So the real problem we have is, so if we recall what we're using here is to come, so we've got quite a fairly good precision when it comes to toroidal field strength, which is nice, but people aren't really interested in the toroidal field. They're interested in the deep-seated field, which is why eventually we're going to move to bespoke 3D modeling, because we use this conversion sort of scaling law. This depends on this thing RM, which is proportional to the conductivity. Now the conductivity is quite temperature dependent. So what we really need is to get really nice. So we can bring our estimates and our constraints into better accuracies, but at the moment, if we're going blind without good phase curve observations, then there's quite a big range where this could be, because the conductivity varies kind of exponentially, not exactly, but kind of. So yeah, these can, if you've got big uncertainties in your daylight temperatures, these can vary, across an order of magnitude, for instance. But if you can bring your observations nice and tight, then you can and get nice measurements. Then again, this gives you nice constraints for your magnetic field strengths.
Great, thank you. And a quick question, there's a lot in this actually that you would have to explain, but maybe could you give us a sense for what the main assumptions are of your models? Jake is asking this on the Slack.
Yeah, no worries. So the shallow water model, what it is we have a 3D, take our 3D model, and then the main assumption is that the atmosphere is thin, which the actual requirement is to do with the Brunt-Weiser frequency being under a certain stratification level. And if you plug the numbers in, it actually turns out to be quite a good observation, quite a good approximation. And we essentially, when we test this back to all the 3D modeling that Tammy, my boss, has done in the past, we actually get really nice matches actually to everything they've done. So we're quite confident that we're working in nice regimes that are well justified and validated.
Excellent. Well, thanks so much, Alex.
I'll quickly add on that. What the shallow water model is you essentially integrate out the Z direction, which makes the model much easier computationally and analytically for all the analytics that we've done. Okay, that's me.
Excellent. Thanks so much. Let's go ahead and move on to Alexander Patrick Stephan, who's going to tell us about temporary hot Jupiters around evolved stars.
Thank you, Brian.
Yeah, you can go ahead and share your screen.
See if I can share my screen.
Sorry, I think I need to stop.
Perfect, thank you.
Okay, and then let me start. You should be seeing the correct view.
Yep.
All right. Thank you again, Brian, and thank you for the previous speakers, and thanks for giving me the opportunity to give this talk today to you all. So the title is quite, so first of all, I'm Alexander Stephan. I'm a postdoctoral scholar at the Ohio State University. This talk is mostly based on work I finished over the last 2-3 years as part of my PhD at UCLA, and I'm continuing as I'm working now at OSU. The title is quite a mouthful, but basically what the basic question I'm trying to discuss here with you is, what can dying hot Jupiters teach us about the dynamical evolution of giant planets? This touches on a lot of the planets I think that we heard about today from the observation side, and here I want to present a dynamical theoretical view on those systems. So first of all, temporary hot Jupiters, what do I mean with this? This is a very basic idea. This is also not a new idea. Gas giants that for most of their lives, for the main sequence lifetime of the host stars, were just simple, cold, long period Jupiters. But then as the host stars evolve, begin to undergo tidal migration, circularization, and tidal shrinking of the orbits until they eventually are engulfed or otherwise destroyed by the star, giving them a cutoff time for the life. This has been thought about by many people over many times, for example, in the context of our own solar system and Jupiter and what its eventual fate would be when the sun evolves. However, this is somewhat tricky when you think about this. It's about Jupiter specifically, because Jupiter is on such circular orbit that the sun would probably, or depending on who you ask, would probably not engulf it. However, if you introduce a little bit of eccentricity, you can get that. So any mechanism that induces eccentricity makes this whole thing much more interesting. Now, I, in my work, mostly focus here on Kozai-Lidov in stellar binaries. So why do I care about stellar binaries? Why should you care about stellar binaries, especially as TESS scientists? Is if we look at just a standard spectral type binary fraction plot from Raghavan et al. 2010, we see that as we go to more massive stars, to OBA and F, we see a very high binary fraction generally, or companion fraction. And of course, these are bright objects, and many TESS targets are located in this area. So chances for these to have companions, chances for these to be undergoing some sort of Kozai is high. So what is Kozai-Lidov? Just really quickly, the basic idea is you have a triple system, a hierarchical triple system. In this example, you have a star, its planet, and then a distant secondary star as the outer companion. Such a configuration is, if it's hierarchical, is long-term stable, but the inner and outer orbits exchange at angular momentum, and you get over time oscillations in eccentricity and inclination, as you show here in this plot. In the bottom, 1 minus eccentricity of the planet over time, in the top inclination over time. And depending on exactly the parameters of the systems, you get some really interesting evolution, as you can see here in the red curve, with extreme eccentricity spikes and inclination flips. That's called the eccentric Kozai-Lidov, or you get some fairly run-of-the-mill evolution in the blue curve. Now, going back to hot Jupiters and what I call the temporary hot Jupiters. Imagine an example system. You have a Jupiter at a couple AU distance from a star. It has a distant stellar companion, and it undergoes some eccentricity oscillations over time. Here I show this example plot over time. The black shows the planet Pierre-Alexis, the blue shows the planet semi-major axis. And for the first couple 100 million years, not much is happening. Things are oscillating. The planet is never close enough to its host star, though, to undergo significant tidal interactions. That changes as the star ages, as you can see here with the stellar radius curve in magenta. Eventually, the star reaches the postman sequence phase, becomes the red giant, and then tidal effects become much stronger. This planet starts spiraling inwards, first slowly, but then very rapidly over the last few million years of the system. And then in this phase, this planet, both because it becomes closer to the star, and because the star is now inflated and much more irradiates the planet much more, this planet is now a hot Jupiter, just at a much wider orbit than what we usually think of for hot Jupiters. I've studied this fairly extensively, doing a whole population study, trying to understand the kind of the features of these kinds of temperate Jupiters you would see on various stages of stellar evolution. So there's a lot going on in the plot here, but what it's basically just showing is, for a given temperate Jupiter, what it is, its death location in the stellar radius, planetary period space, or planetary eccentricity planetary period parameter space, its death location when it gets engulfed by its planet. So what kind of parameters would you see just before this planet dies as a temperate Jupiter? And in the color code just denote various stellar evolution phases. The one thing I want to point out here is that you have residual eccentricities even just before these things die, even though they undergo massive orbital migration through tides. Now, looking at TESS, I've been for the last couple of years since I've finished the first part of this work in 2018, been looking out for it. So TESS observations, if we can see examples for this, and there are now at least a dozen and including with some of the objects discussed in this panel, probably like 24 now, objects that I would consider candidates for this scenario. At least one of them, the very first one by chance, by Wong et al. 2019, was a confirmed binary, a visual binary. I think some of the others have at least tendencies to show some evidence for binaries. So there is now a population of these from TESS observations. Now, what are some of the characteristics that we can see from these objects listed? So, as my models predicted, a lot of them still have residual eccentricities in the 0.1, 0.2, 0.3 range. The masses, of course, there must be a little bit more massive than solar because these are stars that are evolving off the main sequence, or have already left the main sequence in some cases and have become red giants. The orbital periods, they cannot get, of course, super close. They cannot become ultra short period planets because then they would hit the star. But they are basically as close to their star in many cases as possible physically, with orbital periods of order 1 to 3 to maybe a couple tenths. And of course, a lot of these planets have been inflated due to high irradiation. But as we also heard in previous talks, there seem to be planets that are on these that I would classify as these objects, but that haven't been highly irradiated, maybe because they have just arrived at these locations. Some of the things that I've predicted, but that still need to be determined if they're real, are there stellar companions? One example definitely exists, but giant planet or brown dwarf companions can also work. So it's a little bit more wavy, that requirement. But if it is a thermodynamical origin, at least you would expect spin orbit misalignments. So spin orbit, Rossiter-McLaughlin, follow-up observations in the future, going to be very important to determine if this is one of the contributing or the contributing mechanism to forming these objects. And you, if think about the effects on the star itself, you should expect increased spin from tidal interactions. There are some indications present. So what can we learn? Just as to wrap this up, what can we learn from temporary hot Jupiters? As they are extremely radiated and inflated, potential atmospheric studies, some things that have already been mentioned in previous talks. These are very important. Maybe even just from outflows, because these planets are so heated up that they might just be starting to be disintegrated by the host stars. As their lifetime depends completely on the tidal strengths and modes in the planet and in the star, it's very important for us to observe these to learn more about stellar tidal forces. And as I mentioned, the interactions with a star should produce either very rapidly rotating giant stars or subgiant stars, or simply very wacky rotating or wacky stars that produce, for example, outflows. This is going into like too much of a different topic. There's a system V Hydra that people might want to check out, because it is one of those scenarios where maybe a planet is scraping by, scooping up some material and shooting it out as it's in its death throes of being engulfed by the star. And this is a very eccentric object. All right, just to summarize, temporal Jupiters. Actually, I'm just going to leave you with my summary slide because I think I have run out of time.
Great, thanks, Alexander. I'm going to encourage folks to ask questions for Alexander. You have already, Alexander, a few questions on the Slack, so let me encourage you to go ahead and answer those there.
Gotcha.
We're going to take a 3-minute break here and come back at 50 after the hour. So 50 after the hour, we'll come back and start on the next session. Thank you very much, everyone. Okay, folks, hope you had a chance to at least hit the restroom if you needed to. Let's see. Next up, we have Pierre-Alexis Roy, who's going to tell us about Sub-Neptune TOI 1824b.
All right. Is everything working?
You got it.
Great. So yeah, hi everyone, I'm Pierre-Alexis Roy. I'm a PhD student from the University of Montreal working with Bjorn Benneke. I'm really happy to be here today and have the opportunity to share our work on the curious nature of the hot and dense sub-Neptune TOI 24b, a stripped Neptune mantle or a massive rock in a hydrogen envelope. This work really is part of the effort to try and characterize sub-Neptunes and understand their nature. So that's where we will start. Sub-Neptunes have really been nicely highlighted by the Kepler mission and by this now famous figure from Fulton in particular in 2018, which shows the number of planets per star as a function of the planet size for close-in exoplanets. And we nicely see the Sub-Neptune bump and the super-Earths separated by this radius valley. And at least experimentally, it seems like these sub-Neptunes, they are the most frequent outcome of close-in planet formation. But despite this, there is still much we don't understand about their nature, their formation, and their diversity. And this is in part due to the fact that most of the observations we got so far was in transit. Most sub-Neptunes were lighter, so they had larger atmospheric scale heights, which are favorable for transit signals. But because of their colder temperatures, clouds are favorable to form in their atmospheres and yield flat transmission spectra, like in the case of JG 1213b. A way to work around this problem of having clouds in their atmosphere is to look at them during their eclipse in emission spectroscopy, which is less affected by the presence of clouds. But the thing is, if we look at this emission spectroscopy metric, which is just a measure of how suited a planet is for eclipse observations as a function of the planet size, we see that in the sub-Neptune regime, we are lacking this target that would strike out as really favorable for eclipse observations. But fortunately, that changed when TESS revealed a new prime target just for that. So it's TOI 24b with a radius of 2.9 Earth radii, so it falls directly in the sub-Neptune regime. It's really massive with 18.5 Earth masses, and it's on this really short 1.4 days orbit. And because of this, it's close to the star and it's heated up with an equilibrium temperature of 1253 Kelvin. And already with just this, this temperature, we see that it falls on our ESM figure as the most favorable sub-Neptune to look at in eclipse spectroscopy. Not only is it really hot, but it's special because of its high density. If I show TOI 24b on this mass and radius diagram, we see that compared to other sub-Neptunes with similar size, it's much heavier. For example, compared to GJ 1214b, which has a really similar radius, it's 3 times more massive in the case of TOI 24b. So it really raises the question, what is TOI 24b made of? How is this super dense Sub-Neptune so close to the host star? Well, part of the answer lies on the figure I just showed, which here I'm showing TOI 24b with composition curves. And we see that it could be explained by either this rocky core in a 1% biomass hydrogen envelope, but also it's consistent with this 50-50 Earth-like core and water envelope. And then we do not need the hydrogen to explain the properties of the planet. So we wanted to investigate this a bit more. We created this grid of atmosphere models by combining interior models and self-consistent atmospheres on top. And we compared this to the properties of TOI 24b to obtain this posterior relating the water mass fraction in the interior of the planet with the hydrogen and helium mass fraction of the planet. And indeed, that's what we see is that TOI 24b can occupy a range of different compositions, but from a large massive rock in this 1% hydrogen biomass atmosphere to a smaller rocky core in a 40% water-rich envelope and then little to no hydrogen. So to try and make sense of these limiting cases, we try to explain how they could have formed. So in the case of the rocky planet, it could have formed closer to the star, and then was able to accrete a hydrogen envelope. And even if it's on this really short 1.4 days orbit with a strong irradiation from the star, the core is massive enough to supply a gravitational pull that keeps the hydrogen on the planet. But on the other hand, it could also have formed like Neptune, so much further away from the star, beyond the ice line, forming a small rocky core, and then a big mantle of water and ices and metals, and this hydrogen layer on top. But as it migrated throughout the protoplanetary disk and onto its short orbit, it lost the hydrogen layer that was on top. And what we are looking at today is this kind of exposed Neptune mantle that lost the hydrogen. And so we have these two distinct formation scenarios, one that forms closer to the star, one that migrates throughout the planetary disk, and they lead to vastly different planets. And the first thing to try and distinguish between them is to gain information about the atmosphere. So that's what we tried to do with Spitzer eclipse observations of the planet. So we obtained 4 eclipses in each of the Spitzer channels. Here I'm showing the end results of our analysis. So all of the data with the black points being the binned observations and our best fitting eclipse-like curves for both channels. And if I put these results into more context in the eclipse spectrum, first I'm showing our Spitzer data points against black body model for TOI24b for constant temperature. The structure remaining in the models come from the fact that we're using a Phoenix stellar model for the star, which is not a black body. And the first thing that we see is that this channel 2 measurement is much deeper than expected by this equilibrium temperature of 1250 Kelvin, assuming full heat redistribution and 0 albedo. And so we create a grid of self-consistent atmosphere models, assuming chemical equilibrium, and we try to constrain 2 parameters for the planet, which are the heat redistribution factor, which describes how the heat is transported around the planet, and the bond albedo, which is just an index of the reflectivity of the planet. And we see that the measurements favor this high heat redistribution factor, which means poor heat transport. Much of the light would come from the day side, and a low bond albedo, so little to no reflectivity. And so what does that mean when we look at the question that we ask ourselves, which is, what is TOI24b made of? Is it this rock in a hydrogen-rich atmosphere, or is it more of this exposed Neptune mantle in the metal-rich envelope? Well, what we see so far are hints at the hot day side temperature and at poor heat redistribution, but it has been shown before with 3D GCM simulations of Sub-Neptunes that the main effect of having a metal-rich atmosphere is to increase this gradient in temperature between the day side and the night side, and overall increase the day side temperature. So we wanted to test this for ourselves, and we created 2 3D GCM simulations of TOI24b, one for a solar metallicity atmosphere and one for 300 times the solar metallicity atmosphere. And what we see is that the Spitzer measurements are consistent with the metal-rich scenario, and this 300 times solar metallicity model is actually favored by the data with a likelihood ratio of 8:1. So of course, we cannot just yet constrain the metallicity and obtain molecular abundances, but the future for this target is still really bright. With the day side and brightness temperatures we have observed in the study, it becomes really one of the most promising target for eclipse spectroscopy, almost as favorable as GJ436b, for example. And I want to finish by just restating the main points of my talk, which is that TOI24b is really this rare case of a Sub-Neptune that is both really hot and really dense. Spitzer has revealed hints at poor heat redistribution on the planet and metal-rich atmosphere. Both are consistent with the formation scenario as an exposed Neptune mantle, and it remains the most promising Sub-Neptune for further high-resolution emission spectroscopy, namely with James Webb in the coming years. And with that, yeah, thank you very much for your time, and I'm happy.
That was excellent. Thank you so much. I want to ask a question, if that's all right. You suggested the idea that your planet may have started out as a Neptune, lost a lot of its atmosphere, and then sort of migrated into its current orbit. Do you have a sense for how far out it would have had to start in that case, and what the mechanisms would have been to bring it into its current orbit?
I think the scenario that we're going for is that it would have formed, at least beyond the ice line, so that it has a time to has this icy mantle and attract a lot of heavier volatiles, and then during the migration, the hydrogen on top would be stripped away, but the metal content or water content would remain the same and create this really dense planet.
Okay, yeah, I have to think about how much migration you might expect, because I guess if it started out beyond the ice line, it wouldn't have been just sort of simple tidal migration. It would have had to have been, I guess, some sort of dynamical excitation of the eccentricity followed by strong tidal damping.
Yeah, that's a really good point. We have on the eccentricity part, we are constraining a circular orbit with our eclipse times. So yeah, really consistent with circular so far.
Yeah, fascinating. Thank you so much. I'm going to move on to our next speaker now. And again, forgive me if I've mispronounced your name. Our next speaker is Paz Bluhm, and we're going to hear about an ultra short period transiting super Earth around TOI 1685.
Yes, and hi, I would like to share my screen now. Okay, and is this one? Yes. Can you see very well the screen?
Can't see your screen yet.
No? Oh.
You just hit a bright green button kind of at the bottom middle of your screen there.
Oh, that's weird. And now?
I don't see anything. Nick, does she have, does Paz have permission to share?
Maybe I can stop.
Okay, yes. There you go. Perfect. There you got it.
What you can see?
Now we can see your screen. Now we can see your title screen.
Ah.
And the mouse.
Okay, I think it's not the thing that I want to share, maybe. Stop share now. Yeah, shares. And now I want to share screen again. Where is the screen? Oh, I cannot find now the share screen option. No.
Is there a bright green button at the bottom middle of your Zoom window?
No, I cannot see. Oh no.
We were able to see your screen a moment ago, but then it disappeared.
Yes, I think that's super weird at the end, because I want to put enter and then completely disappear. But now I think I'm not allowed to share my screen anymore.
I don't have any control over that. Nick, are you able to help?
Yeah, you should still be able to share your screen. You're still in here as a panelist. So you would still have permission. So you said you're not seeing the share screen button?
No, I cannot see, but maybe I can go and come back and see what happens, because maybe it was just a weird problem.
Do you have a second screen set up, like a second monitor?
Yes, I have one, but
so sometimes that makes Zoom act a little weird.
Yes, I cannot see either there, but maybe I can just do this for 1 second. No, I cannot see nothing. Sorry. Okay,
What would you suggest, Nick? Maybe leave Zoom and come back in?
Yes.
That's one thing you can try. I would also recommend disconnecting your second monitor. Sometimes that helps kind of bring all the windows back into where they should be. Again, sometimes Zoom can react a little weird to a second monitor.
Okay. It looks like Paz just left. So
okay.
Now back. Paz, can you hear us? Are you, there we go. Okay, we can see your screen now. Hopefully that's what you're trying to show us. Although you do seem to be muted.
Yeah, sorry.
Okay, now we can.
I think now you can see my screen.
We can see your browser window.
Yes, yes. Okay.
And now it's gone blank. You may have to disconnect your second monitor, it sounds like. There we go.
It's there, it's there. I think it's there, no?
There we go. Now we can see.
Yeah. Sorry for all the interruptions, guys. Sorry. Well, hi all, and thank you very much, Brian, for having the opportunity to present here today. Well, my name is Paz Bluhm. I am currently a PhD student at Landesdenbarten Heidelberg University in Germany. And today I would like to present my last paper discovery, and was a very, very interesting ultra-short period planet. And this planet is a super Earth that orbits M3 dwarf called TOI 1685. Well, during this talk, I will present that is the least dense ultra-short period planet around an M-dwarf node today, and also is one of the hottest transiting super Earth planets with accurate dynamical mass measurements, which makes it particularly attractive target for thermal emission spectroscopy. Also, I would like to say that the ultra-short period planet is not the only interesting signal that we found in our data. And also during this talk, I will report with moderate evidence that maybe we can find a further non-transit planet candidate in the system. Saying that, here we go. Well, the ultra-short period planet has a period around 0.67 days and was initially discovered as a transited planet candidate in sector 19 of the TESS data. And we confirmed the planetary signal using ground-based photometry and also radial velocity measurements. In the upper left panel of the figure, you can see that the photometric test light curve corrected for systematics with our best fit model for the ultra-short period planet marked in black. As you can see also in the upper left panel is the corresponding phase folded light curve. And in the bottom, you can see the transit light curves obtained with different instruments like LCOGT, Pesto, and Muscat2 in 2 different filters. And here in this case, these white circles are BNet data, but it's shown only for reference. Black curves also is the best fit models, and blue area corresponds to 68 to 95% credibility bands. In all the cases, the lower panel are the residuals of the ultra-short period planet found in this system. And for the radial velocity, this was taken in the Carmenes spectrograph, and we explored the generalized Lom's-Carrel periodogram, or just GLS, which showed in the left figure. And here the first panel is the GLS of the radial velocity data, and here the strongest signal was found about 9 days, and is marked with a green line. A double peak also is visible here in the period range about 19 to 26 days and is marked with a light blue line. And also you can see a small isolated peak, and I mark it in a red color. As we know from the photometry data, the ultra-short period planet is just in this frequency that I marked in red. And maybe we can see that this signal is also shown or pop up in our radial velocity data. But okay, now we have our planet, but what is the origin of this 9-day signal and also this double peak presented in our data? Okay, to understand the origin of these 2 signals, we searched for additional information in the periodograms of activity indicators that Carmenes pipeline provides. And this is showing the remaining panels. And these indicators comprise the chromatic index, differential line width, H-alpha line, and others that you can see there. And you can see that the double peak signal marked with this light blue is also strong in other panels. And for example, in panel G, or the line width, is the strongest peak, which may indicate that maybe this signal is related to stellar activity. But what happens if we want to explore the stability of these signals? And for that, we perform this stacked Bayesian GLS periodogram for the radial velocity data, and you can see these stacked periodograms in the right figure. Here, the main idea was to stack the radial velocity periodograms by subsequently adding observations and recalculating the periodogram. And the final SBGLS periodogram was made between 0.5 to 40 days after subtracting the ultra-short period planet signal. Here you can see that the 9-day signal showed the first probability maximum around 44 days, and then tends to monotonically increases, who is expected as a Keplerian signal. On the other hand, the double peak signal also showed the first probability signal, the probability maximum after 44 measurements, but then tend to decrease for some time. And this kind of incoherence is characteristic for non-planetary origin. Due to the evidence that we have for activity indicators, we can attribute this to the stellar rotation. But okay, now we want to move to model the radial velocity data. I don't want to put too much details in this part, but due to that we have 3 different signals, we want to explore by model comparisons what happened and if we model different models, of course. And for that we used the tool Juliet, which allows fitting the data and at a given prior volume and searches the global posterior maximum based in the evaluation of the Bayesian log evidence. And you can see in the table and all the model comparisons. And due to the double peak structure could be related to stellar rotational period, we investigated what happened if we include a Gaussian process here and to account this signal. And for that, we choose the called quasi-periodic GP kernel due to its widely used to model stellar activity signatures. For example, and you can describe some stochastic physics process occurring in the star, like the exponential growth or decay of some active regions. And this is widely used in the literature. Well, saying that, we choose, based on the criteria described by Trotta in 2008, and we decide that well, the best model in our case is the one circular planet plus GP by model comparisons. But also, if you notice the signals that they have more than 3 signals, and also has a slightly bigger comparisons, and maybe we cannot directly discard the 9-day signals here present in our data. But okay, we select as our fiducial model this one circular planet plus GP. And finally, in order to obtain precise parameters, we perform a joint fit. And for that, we use also Juliet. And in this case, we used all the mentioned data from photometry and radial velocities. And you can see in the table the derived planet and physical parameters of TOI 1685b. And in this case, the figures shows the full radial velocity model and the phase for the radial velocity curve for this planet. And the color code is exactly the same that I show for the photometric data, but in this case, the orange line plotted in the full model represents the quasi-periodic GP. But okay, now go to the more interesting part. Put our planet discovery in context. Well, the left figures show our discovery, our planet, in the context of all known exoplanets from NASA Exoplanet Archive with radius less than 4 and bulk density less than 15. And the known ultra-short period planets are shown in black with error bars, and the blue circles represent the ultra-short period planets around M stars. And the blue-red star is our target or our planet. And you can see that this is the 3rd known ultra-short period planet found around an M star, and also is the least dense of these 3. In the right figure, you can see the mass radius diagram with a comparison of the physical properties of our planet with compositional model from Zheng et al. And this diagram reveals that this planet maybe is consistent with a bulk density composition of 50% water and 50% silicates. And also, we want to compute some metrics in order to estimate the suitability of our discovery and try to see what happens in the characterization of this. And you can see of the top panel of this figure show the emission metrics for exoplanets with measured masses, either by radial velocities or TTVs, with radius less than 3 Earth radius. Planets with emission spectroscopic metrics on order or above the value of the planet GL 1132b, and which is considered this like a benchmark rocky planet for emission spectroscopy, are separated with this horizontal dotted line. Here, we estimated the emission spectroscopy metric for our discovery about 14, and you can see that it's one of the hottest members of this kind of tiny group of small rocky planets, and is suitable for emission spectroscopy. And in the bottom panel, you can see the transmission spectroscopy metrics for all the small exoplanets. We excluded, of course, here the planets with radius smaller than 1.5 Earth radius, just to make the metrics more comparable. And in this context, a favorable transmission metric value of around 90 or higher is very well for transmission spectroscopy, and we found a value very close to this value. We found 86, in fact. And finally, and this is my last slide, an equilibrium temperature of TOI 1685b is estimated to be about 1070 kelvins, which is a little bit larger than 800 Kelvin temperature threshold. And here we don't expect that we have a surface like, a thick atmosphere. But if you look at this plot, you can see that our planet discovery doesn't follow that prediction, because we have a less dense planet, and you can see here that maybe this planet also has a still substantial atmosphere. Okay, saying that, thank you very much. I would like to leave my conclusions here. Yeah.
Wow, what a fascinating system. I'm going to direct you to the Slack. I've posted a question. There's a couple of questions in the Slack for you already. Yeah, do what you can if you can answer them. What an interesting system. Somebody poses so many questions.
Yeah, it's very interesting system. Maybe I just can answer there in the Slack, because I know that I take more time than usual, but it's okay.
I think, yeah, the Slack is really good because it documents the answer, and then other folks who weren't able to attend.
No problem.
Exactly.
Okay,
thank you so much.
Very much.
Okay. Our next speaker is Luca Malavolta.
Hello, can you hear me?
Yes, I can hear you.
Okay, I'm going to share the slide and try this thing that was suggested in the tutorial, so you can see myself during the slide.
Perfect.
So I hope the audio is good. So I'm going to talk about ultra-short period lava worlds from an observational point of view, because I work more on observation than theory. So I'm just going to introduce this new planet and let other people in the future doing more studies about that. So lava planets are a kind of a subcategory of ultra-short period planets. Are planets where the surface is just molten rocks. They may have magma oceans, rock, water, vapor, atmosphere, and supersonic winds. So any kind of hell conditions. I say it's just a category because only the planets that have at least an equilibrium temperature of 1500 K can have such a condition. Usually you can find this condition only on the shortest period, ultra short period planets around the FGK stars, because then M starts to become too cold to properly warm the surface. So until now, there are only a very limited number of ultra-short period planets that have a phase curve observed with either in the infrared with Spitzer or in the optical, such as Kepler observation, Kepler 78 and Kepler 10b, or K2 observation. So K2 141 is actually one of my favorites, as you can imagine. Also because it's the ultra-short period planets with the shortest period and known density, which are rocky density. So having the phase curve in the optical, it means that the surface of the planet is really hot. if the thermal emission must be considerable even in the optical passband and not just in the infrared. You can find some more modeling about this paper recently submitted, Nguyen et al. 2012. If you're 2020, sorry, if you're more interested in theoretical aspects about the possible surface of this planet. So now I'm going to introduce a new ultra-superior planet, which is taking the record of the one with the shortest period, and I'm going to show you also the mass determination, and it is TOI 2431b. So this object has been detected by TESS in December 2020, so quite recently in sector 31. It has a period of less than 6 hours, so 0.22 days. So it orbits very close to its star. So we do the usual job of redetermining the stellar parameters using all the information available to us, photometry and Gaia parallax, and we also did a new fit of the light curve in order to have a more precise estimate of the radius of the planet. Pay attention that many times on exophore ultra-superior planets have quite a higher value than the one that you actually get by doing the fit. So we don't know why this is happening, but you should always double check the values that exophore is giving to you, and also be careful if you're using this value to select your targets for proper follow-up. So we used this code called Pierre-Alexis to do the light curve and also radial velocity analysis. For the radius, we obtained 1.38 Earth radius, you can see here, with a very precise determination. So, of course, after getting the radius, we decided to get the radial velocities in order to measure the mass. We went to the Italian telescope, Telescopio Nazionale Galileo, which is hosting up north. You can see up here a photo taken maybe 10 years ago already, when the instrument was still open. The observation was taken as part of the guaranteed time observation. There are other posters in this conference that use this the data from this consortium. Also, you may want to check the Gaia Lacedelli poster, which is about another ultra-short period planet, TOI 561. This one is the least denser rocky planet, which is also an ultra-short period planet. So moving forward, the very nice thing about ultra-superior planets is that within one night, you can actually sample most of the radial velocity light curve. Here, for example, you can see observation of K241. You can see that within the observability window of the target with the air mass lower than 1.2, I mean, when the target is very high in the sky, you can observe both quadratures. So knowing this, you can use a technique called floating chunk offset, in which you take many observations of the target during the same time, trying to cover as much as possible the radial velocity light curve. By doing so, all the other signals that are longer than the 1 day, and they are not too high, so the sum must not be too active, for example, are just absorbed by this offset that you are introducing when modeling each night. So you basically shifting up and down the data gathered during the same night in order to reconstruct the radial velocity curve of the planet. And by doing so, you can get a very precise mass for the planet up to 10 sigma, even if you don't know what is the architecture of the system, or you don't know what is the activity level of the star, assuming that activity level is not too exaggerated. Of course, we're talking about signals that are more or less of the same amplitude of the planet, or maybe even higher, but on longer time scale. So here, for this planet, we did the exercise of comparing the nightly offset results with the result that we obtain using other techniques. For example, using the K2 light curve to model the activity, or using the Reg-Pol framework for the stellar activity, getting basically the same results from the from the planet. So we decided to use, of course, this technique also for our new planets. We've been a bit unlucky here because the planet was discovered near the end of the observational season. So we only had a few hours to observe the target, but luckily it was a short period enough to cover both quadrature and some specific night. And by observing it in 9 nights, we managed to get 31 radial velocities and determine the mass at 10 sigma confidence, maybe a bit higher. We have not been so lucky with the architecture of the system because we have only a sparse sampling, and now we know that there is another planet in the system, but we don't have enough data to determine what is the period of the planet. So there are 2 solutions that have the same Bayesian evidence, sorry, but we cannot distinguish between the 2. These 2 solutions are giving the same mass for the ultra short period planets, which is, by the way, determined using the floating Chong offset method. So, of course, the first thing to do is to put your planet in the mass radius diagram, and we determined that it has a composition quite similar to K241b actually, which is the planet that already showing a phase curve in the optical band of Kepler. So we decided also to check if this planet has a phase curve in the TESS data. So Sanquin did the analysis. He found that indeed with not a high confidence, we can see some signal in the TESS band. The lower confidence is mostly due to the fact that we have a shorter period of observation and the photometry is not as good as the one for the Kepler TESS band. But still, this is a very good sign that the planet is a good candidate for a follow-up observation, for example, with JWST. Another properties that makes this target more suitable than K241 is that the star is brighter, and also the period is slightly shorter, so it will help in taking more observations. And that's all. I told you I was mostly on the observational side.
Great, that was really fascinating. Elizabeth, I'm going to ask you a question. Do you see any evidence for a second potential planet? Oh, I'm sorry. This is for this is for you. In the TOI 2431 transits for TESS.
No, we didn't see any second transit in the LATIO.
And nothing in the RVs then, I guess, as well.
We see something in the RVs, but we cannot decide which one is the correct solution.
I was just wondering if with using the RVs, if you could do a targeted search for a very faint companion, a very shallow transit in the TESS data. So.
Yeah, we hope the targets will be observed in the future with TESS.
Yeah.
So we keep looking again in the future.
And Luca, remind us how bright is this star?
The star is 10.9 B magnitude.
Okay.
So it's still feasible with JWST and of course from radio spectroscopy from spectroscopy from the ground. For transmission spectroscopy from the ground, the problem is that the transit is too short. So basically, you have only like half an hour to gather. You can gather basically 1 or 2 spectra while the planet is transiting. So in this case, the follow-up from the ground is a bit difficult if you want to do transmission spectroscopy.
Yeah, that's really fascinating. Okay, well, that's great. Thank you. And if you wouldn't mind to give an answer to Elizabeth's question on Slack as well, we'd appreciate it. Thank you so much. Okay. Next up, we have Kristine Lamb, who's going to tell us about another ultra short period. And this is a sub-Earth. I'm really interested in this system, a sub-Earth.
Right. I should be sharing my screen.
Yes, now we can see you. Thank you.
Okay, so I can start. Good morning, good afternoon, and good evening, everybody. I'm Kristine Lam from DLR in Berlin, and it is a pleasure to be here today to present an exciting discovery of a dense ultra-short period sub-Earth, which is GJ367b. And before I start, I'd like to thank all the co-authors for their contributions to this work. Currently, this work is still under review, so I'd like to ask the audience here to not share the results elsewhere outside of this conference. So, M12s are the most abundant type of stars in our solar neighborhood. And previous abundant studies have estimated that M12s can host 2.5 small planets with periods of shorter than 200 days. And the advantage of observing M12s is that the transit and radio velocity signals of an Earth-sized planet around an M12 is stronger comparing to an Earth-sized planet around a G-type star. Therefore, observing M12 stars can give us the best chance of finding the smallest possible planets. On the flip side, young M12s can also have enhanced stellar activity, which can make radio velocity follow-up difficult. Okay, GJ367 is a bright hypermotion star that is only 9.42 parsecs away. Using co-added Hubble spectrum for spectral analysis, the results show that the star is consistent with the spectral type of M1, and the stellar radius of GJ367 is just under half of that of the Sun. The target, GJ367, was first observed during TESS Sector 9, and now also available in Sector 35 and 36. Using the PDC SAP-like curve from SPOC pipeline for transit, we've used the PDC SAP-like curve from SPOC and for transit detection and light curve analysis. And using multiple transit search pipelines, we can independently detect a transit signal with a period of just 0.32 days. And the figure on the right on your screen, you can see a phase-folded transit of the planet candidate. The transit depth of this planet is very shallow at only 300 ppm, which would correspond to a sub-Earth ultra-short period planet around an M12. And for reference, the transit depth is comparable to that of Corot 7 and Kepler 10, Kepler 10b. There are 4 seasons of WASP photometry available from the archive. We've done a periodogram analysis, which is shown on the right-hand side of your screen. In all seasons, there's a clear rotational modulations from the light curve. And for each season, this modulation period can range between 44 to 49 days. And an independent autocorrelation function and wavelength analysis also found a rotational period of 48 plus or minus 2 days. From the HARPS data, we were able to measure the chromospheric activity of the star, and the value of the activity indexes log RHK is minus 5.21. We then use this activity rotation period relations for low mass star to determine the rotational period of this star to be 58 days. And this is also consistent with what we found from the WASP data. And we looked at the archive ROSAT data and determined the upper limit of the X-ray luminosity of this star. And the upper limit tells us that this star is not particularly active. So overall, it makes the star a very good candidate for follow-up observations. And to rule out the origin of the signal that could come from a possible nearby eclipsing binary, we obtained a number of seeing limited photometry to check for possible false positives. And a few nights of photometry were obtained on REM and the LCO telescopes. And from these observations, we have managed to clear all Gaia stars within 2.5 arc-minute radius from the targets of being a nearby eclipsing binary. So this supports that this USP planet signal is of planetary origin. And we've determined the contamination to the target light curve from neighboring stars because GJ367 is in a relatively crowded field. And with from the ground-based photometry, we managed to determine the contamination as 9.5%, which is consistent with what was found from the SPOC pipeline. In addition, we've also observed GJ367 using the Zorro speckle instrument on Gemini South. And the star was observed in the blue and red band, and the corresponding contrast curve is shown on in the figure on your right-hand side. And we find that the target star is a single star and there is no companion brighter than about 4 to 5 magnitudes below that of the target star within an angular separation of 1.2 arcsecond. And the target star GJ367 was observed as part of the RV survey by Bonfield et al. 2013. And following the detection of this target, we've also collected additional radial velocity data from HARPS. The figure on the left shows all 105 data points that we've collected. And using these data, we have performed the frequency analysis. And this is shown in the generalized Lomsgargo periodogram on your right-hand side. We can see a peak in the RV periodogram corresponding at 0.32 days. And this signal corresponds to the USP GJ367b. There is no counterpart in the periodogram of all the other activity indicators, so this can confirm the signal is of planetary origin. And furthermore, we can also see a low frequency signal at around 36 days. And we think this is coming from the rotational modulation of the star. There's a further 11.7 day period that we can see from the radial, the Lomsgargo periodogram, but there are no activity counterparts in the activity indicators. So we think it could be a further planet, but unfortunately we didn't have enough data to confirm this. If you'd like to see the most recent analysis of these data sets, please, I'll recommend you to go to see the poster by Elisa during your break later. Okay, so for ultra short period planets, long period radial velocity variation that comes from the stellar activity or long period companions can filter out using this so-called floating chunk offset method, which is already mentioned in the previous talk, but I'll quickly remind everyone how it works. The method takes advantage of the case where the planet orbital period is significantly less in the timescale of the activity cycle. So using this method, multiple measurements are taken over one night, where one can see predominantly the orbital period, orbital motion of the USP planet, while the other variation due to stellar rotation or long period companions are essentially frozen. So when we fit the RVs in our model, the period and ephemeris of the USP orbit is fixed from the transit light curve, while the nightly offset, 0-point offsets of the nightly RVs are allowed to vary. So this essentially acts as a high pass filter where only orbital motions of the USP is detected and the RV amplitude can be accurately measured. And in our joint light curve and RV model, we've applied this FCO method where the HARPS data were grouped into nightly chunks and the nightly offsets of each chunks were fitted. And the joint analysis, as you can see here, was performed by the TLCM code, and the parameters and the errors were estimated with an MCMC analysis. And the joint model of all of these data showed us that GJ367b is a sub-Earth sized planet with a radius of 0.718 Earth radii and a mass of 0.546 Earth mass. And this corresponds to a planet bulk density of 8.1 grams per centimeter cube. And the figure on the right here shows a phase-folded transit light curve of the USP planet. And at the bottom, you see the phase-folded RV curve. Okay. We compared the properties here of GJ367b with other low mass planet in the mass radius plot, which is shown on the left. Each of these exoplanets are color-coded according to the equilibrium dayside temperature. And the dashed lines in the plot are the planet interior models of Zhang et al. Comparing to these models, the USP GJ367b is likely, it's very standout in one of the lower, smallest planets that are known to date. And comparing to the interior models, the planet is likely to be an iron-dominated, has an iron-dominated core with an interior that is similar to Mercury's. On the right-hand side, you see the mass density plot, which shows all the known USP planets with precise mass and radius measurements. And the bulk densities of these low mass USPs are all Earth-like or even denser, which corresponds to interior similar to terrestrial planets and the physical properties associated to how these planets were formed and evolved in extreme environments. And for GJ367b to be so dense, possible formation or evolution mechanisms that can form a high density planet must involve some sort of giant impact scenarios. Okay, here I'm almost done. And to summarize, we have discovered a dense ultra short period planet, which is GJ367b. The planet is by far the smallest planet from TESS, with a precisely measured mass. Density of this planet is corresponding to a predominantly iron core, which is similar to the interior of Mercury. And the target, GJ367, is a very bright nearby M dwarf. So when we looked at the transmission and emission spectroscopy metrics, it's a really standout candidate, which is good for follow-up characterization. Okay, that's all from me.
Wow, just fascinating. Elizabeth, I saw your question. You want to go ahead and ask that?
Sure, it's very similar to yours. So I want to know if, because I'd love to find one of these things, there any possibility this could be one of those stripped fossil cores of a giant planet? Could that be the source of the density?
We actually looked at the possible remnant of Jupiter scenario and compared this to a photoevaporation and how much mass is lost due to photoevaporation over time. We found that photoevaporation alone cannot strip all of the atmosphere or enough mass to form this sub-Earth planet. So either this is coming from a even smaller planet, maybe a Sub-Neptune, or some other evolution scenarios would have to explain this.
Cool, thank you.
Yeah, that's fascinating. It's maybe worth pointing out that I think the orbital period for this object is within the Roche limit for a Jupiter. So you might expect that such a planet would not have done a sort of standard photoevaporation of its atmosphere, but would have actually lost it through, rapid overflow, Roche overflow.
Right. Yeah.
Another question on the Slack we have: are there any plans to concern the presence or lack of a thick atmosphere for this planet?
Yes, of course. We'll love to prepare proposals to observe the presence or lack of presence of an atmosphere. But at the moment, we tried to apply for time on JWST, but unfortunately that was not selected. But so maybe in the future, definitely, I think it would be a good candidate for that.
That's really fascinating. And I see we've got one more question on the Slack. Congratulations on a really nice result. Do you think there is a venue for fitting nightly offsets while also correcting for short-term stellar activity with Gaussian processes or detrending with activity indicators?
Yes, I think you can definitely fit Gaussian processes with the activity indicators to model the RV variation induced by the stellar rotation. We sort of try to do that. I have a backup slide. So in an independent method, which uses a Gaussian process to model the variability in the RV data, initially we used the TESS light curve to try to constrain the modulation period of the star. But unfortunately, of course, as we've seen before, the rotation period of the star is 40 days or little more. And one sector of the TESS data was only 27 days, right? So we can only put a broad log prior to constrain the periodicity of the GP model. And but using this method, we get a consistent K amplitude as the FCO method. But yeah, in the future, when we get more data, then we can do this so-called multi-dimensional GP process to model the whole data set.
Yeah, that's great. Well, thank you so much. All right, we have a few minutes here scheduled for a discussion. So before we dive into that, I just want to remind everybody that there's a talk on the Juno mission today at 11:45 Eastern, 8:45 Pacific, 15:45 UTC in, I believe, this room, in room 1. So if you're interested in learning more about that,
that's now, Brian.
That's right now. So, all right, I guess we'll cut our discussion.
Yeah, Brian, we will start the Juno mission in a 5-minute delay.
Oh, okay. Well, there you go. Perfect. 5
Just
minutes.
to give people some time to, calm down.
Right, right. So then rather than having a full-on discussion here with all the panelists, I just want to propose again this set of questions that I sent out over email and ask you to think about this maybe over the Slack channel. I think these ultra short period planets are really fascinating. They're of course some of the first kinds of planets that we have been detecting in other solar systems. And so they're very different in many ways from planets in our own solar system. But what I'd like to think about is, what can they tell us about our solar system? What are they telling us about the way our solar system may have evolved, and maybe where our solar system is going? So to think about these less as just kind of strange, weird systems that are interesting in their own right, but more to think about what they tell us about planetary systems more generally. So I'm just going to put that idea out there because I don't want to take up the room when they're prepping for the next session. If you have any thoughts about that, I would love to read them on Slack. As well, if you had questions that I related to you from the Slack channel, please, I encourage you to go to Slack and answer those questions, even if you answer them over the Zoom window here. And thanks again so much for attending. I want to make sure that I indicate that we had more than just myself organizing. We had actually a big team of folks who helped organize this session. So I'm just one of them. So thanks again so much for participating. Thanks to all the speakers, just really fascinating talks. We'll go ahead and stop here.
Okay, thank you, Brian. And for those who did session hopping, as I did in the last 2 hours, the recording of all the sessions will be online probably tomorrow. So now we will move to the Juno Mission talk. We will start in a few minutes, so if you want to go get some water, coffee, or stronger beverage, now is the time. Hello, Stephan. Thank you for joining us. Good morning.
Morning.
So we will start in a few minutes, but you can go ahead and share your desktop, see that everything is working okay.
All right, let's give it a try anyway. Okay, do you see the title slide?
Yes, looking great.
All right, then I guess we're ready to go. We can just wait till people are.
Yeah, let's we'll wait.
That's interesting. My PowerPoint is just changing slides all by itself. That's all right.
That's what it wants.
I'll just keep an eye on it.
Okay, so we'll wait a few minutes until 11:50 Eastern, 8:50 Pacific, 3:50 UT, 5:50 Central European Time. I can go on.
I'm pretty sure there's an island somewhere where it's half an hour off.
I think it's not an island. It's somewhere in Asia. But,
okay.
Yeah, or maybe there is more than one half an hour time zone. But while preparing for this conference, I actually discovered it and already forgot exactly where it is. And for the audience here, since this is an off-topic talk, it's not an integral part of the TESS science that we are focusing here during the week. Feel free to invite some colleagues or family members if they want to watch this talk as well.
And bring questions, because that's going to be the fun part.
And bring questions. And about that, questions go to the general Slack channel in the conference workspace. speaking of time zone, Leslie Rogers just reminded me that Newfoundland is half an hour off.
Okay.
Okay, so welcome everyone. We have with us Steve Levine from JPL. He's the Juno Mission project scientist. And he has agreed to give us a tour of, let's say, how to explore a planet up close by literally flying them. So Stephen, thank you very much for agreeing to do this. I told you that before, but of course, if this was, let's say, normal times, we would host you at MIT and fly you over and meet in person. But unfortunately, we cannot do that. Hopefully, we can do that sometime in the future. Congratulations for this very exciting and amazing mission. I know that tomorrow you're celebrating 10 years for the launch and a little over 5 years of actually being at Jupiter. Okay, and again, for the audience, questions are on the general Slack channel. And yeah, Stephen, I think you can just, you can just take it away.
All right, thanks for inviting me. It's a pleasure to be here, even if it's only virtual. And as I said, or as Ari said, I'm the project scientist for Juno, which is a spacecraft that's orbiting Jupiter. I won't read everything there on the slide. The main thing from the point of view of the science is Juno is in a close polar orbit about Jupiter. So we get a very close-up look at the planet. We've been doing that since 2016. We just recently completed our 34th Science Perijove pass, which is the last Perijove pass of the prime mission. So we're starting extended mission, in which we'll do a few other things. The main idea has been to try to understand the origin, interior, atmosphere, and magnetosphere of Jupiter. So Jupiter is surrounded by radiation belts. We've had other spacecraft go to Jupiter, but they've stayed far away, so they didn't get eaten up by the radiation. What we're doing is diving underneath those radiation belts by looking at the composition of the atmosphere and the interior structure using gravity measurements. We try to learn about the origin of Jupiter. We look at how the material moves within the planet, map its gravitational and magnetic fields, study the atmosphere with microwave radiometer that can see through the clouds from Earth. You really can't see much of Jupiter other than the tops of the clouds. And because we're in a perfect orbit to do so, study the magnetosphere of Jupiter, the interaction of the planet's enormous magnetic field with all the fields and particles and waves going on, and in particular study the aurora in the north and south. And as you may already have deduced, I'm going to try to rush through as much as I can here and save time for questions. So the biggest question, of course, is what have we learned? And the shortest version of that, I would say, is what we've learned is humility. Almost everything we thought we knew about Jupiter that we were able to do new measurements about gave us a surprise. So perhaps a better way, or at least a more comfortable way of looking at that, is to say it's a whole new Jupiter. We've looked at Jupiter in a wide range of different ways than had previously been measured. We're measuring the gravity field because we're flying so close to the planet. We're measuring the magnetic field, making a full map from close. We're using microwave radiometer to see beneath the clouds and looking at the deep atmosphere. We flew over the poles of Jupiter for the first time and got the first good look at the north and south pole of Jupiter. We looked at the aurora of Jupiter with fields and particles instruments, in situ instruments, and remote sensing instruments to look at the aurora in a new way. Every single one of those gave us a big surprise. The short version is anything we measured that hadn't been measured before was a surprise. So I'm obviously not going to have time to talk about all of the surprises and everything we've learned. And I've picked out half a dozen or so of what I see as the biggest surprises or the most interesting surprises. And I'll just talk about each of them a little bit. And then hopefully with questions at the end, we can get into greater detail or talk about some of the other things we've learned. The first one we saw was we see clusters of cyclones around the north and south pole of Jupiter. The north and south pole of the planet, the northern and southern hemispheres of the planet look very different in the visible and the infrared than they do from the Earth, where all we get is an equatorial view. The deep atmosphere is not well mixed. So virtually everybody thought before the spacecraft got to Jupiter that when you got below the depth of the water cloud, about a pressure of 10 bars or so in Jupiter's atmosphere, that the planet would more or less look the same in all latitudes and that things would be reasonably well mixed with depth. That's totally wrong. We knew there should be a dense core deep inside Jupiter, and the estimates were 3 to maybe 20 times the mass of the Earth. So from a percent to several percent of Jupiter's mass. But what we found instead is, yes, there's a dense core and it's a comparable size to what we expected in mass, but it's extended, it's dilute and fuzzy compared to what we expected to find. And we're now looking to see whether the gravity can give us any signature of perhaps something even denser in the middle, or try to explain what's going on. The most striking feature on Jupiter seen from the Earth is the belts and zones. Those orange and white stripes are zonal jets. They're jet streams traveling across longitudes, each at its own latitude, back and forth across the planet. Well, we didn't know the depth of those, and in general, many people thought they would be shallow. Well, they extend to about 3,000 kilometers, which is a very interesting depth, and I'll talk about that in a few minutes. We mapped the magnetic field in detail for the first time, and what we found is a magnetic field that's much more complex than expected. And that's particularly interesting because the complexity of the magnetic field implies contributions to the magnetic field that are shallower than the liquid metallic hydrogen down in the middle of the planet that was thought to generate the magnetic field. And it's still thought to generate the bulk of the magnetic field. Furthermore, we see features sheared by deep jets. We actually see that the magnetic field is not constant with time when we compare the magnetic field we see with the magnetic field measured from 30 years ago by other spacecraft, taking advantage of the greater detail we have now, of course. We discovered shallow lightning in Jupiter. Lightning so close to the top of the atmosphere that it's above where any reasonable expectation was for finding water clouds. So that implies lightning that doesn't require liquid or solid water to generate it, or it implies some other mechanism. And as you'll see, we have a potential proposed mechanism for what's causing that lightning. And finally, as I mentioned, we're examining the aurora, and we see aurora that are very different from what's seen on the Earth in terms of how they're generated and some of the details. All right, well, let's just show a few of those surprises, and then hopefully we can rush along and get to questions, because I'm hoping we'll spend a lot of time on questions. So this is an infrared image of the North Pole. The first discovery that showed us the circumpolar cyclones was actually in a visible image, but I like the infrared better because you can see the entire thing at once. You don't have to make a montage of multiple shots to get daylight at various times, and you can see a lot of detail in the infrared. So what you see is a cyclone at the North Pole and a pattern of 8 circumpolar cyclones in a rectangular shape, and that shape has stayed essentially constant over the 4.5, almost 5 years of the Juno mission. So what we see is what we're thinking of as a crystalline structure in vortices at the North Pole, and a different crystalline structure at the South Pole. We've seen a little bit of jockeying of position of these circumpolar cyclones. We saw once momentarily at the South Pole, a sixth cyclone sort of joined the group and then was pushed out again. But basically over the course of the several years of the mission, we see this same pattern of circumpolar cyclones in the north and the south remaining constant. Get my, there it is, just another view of that. Okay, the deep atmosphere. As I mentioned, Jupiter's atmosphere is not well mixed. So below the water cloud, where the sunlight can't reach, where you're looking at a giant ball of fluid, what was expected was that the atmosphere would be more or less homogeneous, particularly across latitude, and reasonably well mixed with depth. Well, that, as you can see from this map, is totally wrong. Now, the microwave radiometer measures a product of opacity and temperature, and Jupiter's hotter on the inside than the outside. So interpreting the data can be complicated. In this case, the map I'm showing you assumes that it's all due to opacity and is dominated by ammonia, which is what's expected to be the dominant absorber at this frequency. But regardless of whether it's ammonia or there's temperature variations or something else, what you can see is that the structure, there's substantial structure as a function of latitude. You're looking at latitude on the horizontal axis, pressure into the atmosphere on the vertical axis, and we've capped it. The microwave radiometer penetrates as deep as perhaps 1,000 bars, but it's hard to interpret below around 100 bars. So what we've done is arbitrarily really required that at a few hundred bars, the atmosphere be uniform as we expected before Juno got there. But even with that constraint, you're unable to fit the data with anything that's uniform above that. So you can see well below the water cloud. The water cloud should be about 5 to 8 bars. You still see variation with latitude. And we also see this strange ammonia deficit where we have ammonia sort of as expected up at the top of the atmosphere. It starts to go away. You have less ammonia down around the depth of the water cloud, maybe a little bit lower. And then below that, ammonia climbs back up again, except at the equator and at this region a little north of the equator. And if you look closely, it's not even symmetric. It's not exactly at the equator. It's a few degrees north of the equator. So as I'll mention later when we talk about the shallow lightning, we have an idea now, having seen that, that it's somewhat speculative, but suggests maybe we can come up with an explanation for how this could happen. And it centers around the idea of mush balls, which is that if you mix ammonia and water, you change the freezing point. And if you have the equivalent of hailstorms, but on a Jovian scale, you can carry that frozen ammonia and water mixture up high and down low and get well below the water cloud and cause some of the effects we see. Another important result, as I mentioned, is the deep core. The central core of Jupiter, based on the gravity measurement, appears to be diluted and fuzzy, perhaps stretching out to as much as about half the planetary radius. The gravity measurement gives you the deep core because as the spacecraft falls very close to the planet, the speed of the spacecraft tells you the gravitational signature from the planet. And with Jupiter rotating once every 10 hours, so twice as fast as the Earth, but 300 times the mass, the density structure of the interior contributes, combined with the rotation, to a distortion in the gravity field that you can measure. So we're left then with, how do we get a core that dilute? One of the theories that has been suggested is some sort of giant impact that potentially could work, but of course it's a little bit ad hoc. There are other theoretical concepts people are still working on, but the bottom line is we have the observation and we're still trying to catch up with an explanation of how Jupiter came to look like that. The belts and zones are 3,000 kilometers deep. So 1% of Jupiter's mass, 3 Earth masses, is in those jet streams. Furthermore, 3,000 kilometers is a really interesting depth, because if you look at what happens at how hydrogen behaves under pressure, 3,000 kilometers is about the depth at which the atmosphere starts to be a little bit conductive of electricity. Think of it as comparable to salt water. So there's a strong suspicion that the depth of those belts and zones is tied to Jupiter's magnetic field, that the magnetic field is perhaps inhibiting the belts and zones at depth, that is defining the depth at which they can reach. This measurement comes primarily from the gravity. We see microwave radiometer measurements that are consistent with it, but microwave radiometer doesn't see as deep as a few thousand kilometers. And the local gravity effects of the belts and zones are what are determining our estimate of the depth. And then tied to that, as I just mentioned, because of the interesting fact that the depth of the belts and zones matches up about with where you'd expect the magnetic field to start to make a difference, is our measurement of Jupiter's magnetic field shows it to be much more complex than expected and in really peculiar ways. So if you look at the south pole of Jupiter, or the southern hemisphere in general, it looks more or less dipolar, not in kind that different from the Earth's magnetic field, about what we expected it to look like. But if you look at the northern hemisphere, it's not all that dipolar at all. There's all these bumps and wiggles in local places where the magnetic field is stronger or weaker. At the equator, there's what we're now calling the Great Blue Spot, a place where the magnetic field has a sort of a hot spot, the direction of the magnetic field looking down into the planet, radial magnetic field. And when you examine the actual details of the magnetic field and compare with older measurements, even though they were limited, you get a pretty definitive result that the magnetic field has changed over the last 30 years. And in fact, you can estimate about how it's changed. And the way it looks is that the zonal winds are advecting the magnetic field. The magnetic field is being sheared by the winds of Jupiter. You can see the prediction here for what it will look like in 2060. That exaggerates it enough that you can see what's going on as those belts and zones take the winds take the field in opposite directions. It takes a structure like the Great Blue Spot and shears it and breaks it up. And then, as I mentioned, we see shallow lightning. So we looked at Jupiter in a new way using the star camera on the spacecraft to look at the upper atmosphere in the dark. So it's a camera designed for navigation, but that means it's particularly good at looking in low light conditions. So looking at Jupiter in low light conditions is a strange thing to do. It's one of the brightest objects in the sky. But we had the opportunity to do so and made some really interesting discoveries. So in particular, we see lightning happening on Jupiter. Jupiter was known to have lightning, although our microwave radiometer has shown a lot more lightning than was expected and in different ways. But the SRU, the Stellar Reference Unit, the star camera, can see the lightning in the dark when it's fairly small, and has actually discovered that in addition to the lightning flashes that were known about at altitudes around where the water cloud is, we see some tiny lightning flashes that must be happening at an altitude much higher than that. If they were happening deeper, they'd spread through the atmosphere and we'd see them as larger, weaker flashes. So it tells us that lightning's happening on Jupiter at an altitude that's much too cold for liquid water. Previous models of how lightning works suggest that there ought to be solid, liquid, and gas all together in order to get lightning, to get the charge separation that causes lightning. And this combined with the microwave radiometer results of the atmosphere that showed all that structure and strange deficited ammonia recovering at depth, has led to a theory that's starting to look like it's going to work, a model that says what happens is ammonia combined with the water makes a sort of antifreeze so that the water ice stays frozen at a different depth. And you get hail but hail in the form of ice on the outside and this ammonia water liquid mixture on the inside that can go up and down to greater pressure range, generating the high altitude lightning, and perhaps also explaining what's going on, or part of what's going on, that we see with the microwave radiometer, where the atmosphere is more complex at depth and has more structure. And then finally, there's way too many surprises and things to talk about them all for the auroral investigation in the fields and particles, but I'll just point out a few of the highlights that I find particularly interesting. You see an example shown here in the middle right of the plot. You see that the polar cap aurora, which had been seen from Earth, but only during the daytime because the Earth is on the sun side of Jupiter always, actually light up much more in the daytime than at night. When you go fly over the poles and take images, you can see that that polar cap calms down quite a bit in the dark. And there was no previously known explanation for why that should be connected to the local time. That's something being investigated. We see megavolt potentials over the polar caps. We see acceleration mechanisms for the particles that stream down the magnetic field and hit the upper atmosphere that are different from the mechanisms that drive things on the Earth. Sometimes the same mechanism, but it's different level of importance. We found an equatorial radiation belt of energetic ions very close to the planet, near the equator of Jupiter. We see that the tail from Io, the auroral tail, is split into two. So if you think about Io orbiting Jupiter and all the stuff going on with volcanoes and so forth and how it interacts with the magnetic field, then you trace those magnetic field lines down to the planet. We always knew, or we knew for many years, that there's a bright spot in the aurora corresponding to the magnetic footprint of Io. What we didn't know until Juno did the measurement is that bright spot is split into multiple bits and pieces, as seen in the lower left of this picture, and that when you follow the tail, the trail of where that spot has been, which is not the motion of the moon, but rather the magnetic signature from the symmetry in the magnetic field, you see that the tail of Io is split into two. So that was another big surprise. Lots of other things we could talk about. We have some interesting things to say about citizen science that we've done with Juno and the education. I can talk about the extended mission. And of course, I can take questions about the various things I've already mentioned or any other topic related to Juno. But it seems like now would be a good time to stop and allow lots of time for questions.
Okay, thank you, Steve, for that nice tour. I'm checking the Slack channel. Again, the questions should go in the general Slack channel. Question by Hans Jelzen. You estimated the depth of the cloud bands to go down to 3,000 kilometers. Do you have data for the Great Red Spot? Will the magnetic field play a role for the Great Red Spot? And I think everyone knows what the Great Red Spot is.
Right, really interesting question. And the answer of do we have data is yes, but we don't have the same kind of data. So the Great Red Spot is small enough that the gravitational signature is weaker. We have a paper that I hope will be out soon that says something about the depth of the Great Red Spot from the gravitational signature. We have shown the microwave signature that shows that it goes as deep as we can see in the microwave, so at least a few hundred bars. That tells you then that the Great Red Spot goes quite a bit deeper than most previous models, although there have been a wide range of models for what the Great Red Spot could look like. And then, as I said, stay tuned for the result from the gravitational signature. Remember, to do that, not only is it smaller than an entire ring around the planet, but of course you have to fly over it. Each perijove pass is a different longitude, chosen to make the magnetic map. So they're different magnetic longitudes, but the great red spot drifts around the planet. So we only had a few passes where we came sufficiently close to get that signature. And then the question of whether the great red spot is tied to the magnetic field, it's clearly not tied to the magnetic field in a simple, straightforward way. And you can tell that because it does drift around the planet. Those belts and zones, if I go back to the picture with the little animation, those belts and zones move left and right across the planet. And the great red spot is in between a belt and a zone. And it sort of rolls along like a marble caught between the belts and zones. And you can see it drift around the planet relative to the magnetic field. So it can't be some sort of spot in the magnetic field tied all the way up to the surface, or it would be wrapping itself up around and around the planet. Now, could it interact with the magnetic field in some other way? Yeah, that's certainly a possibility. As I mentioned, the 3,000 kilometer depth for the jet streams is a very interesting depth. It's led to speculation that what's going on is the bottom of the jet streams is limited by interaction between the magnetic field and the atmosphere. So you could imagine that some more complicated interaction either spun off the great red spot or is related to its lifetime or things like that. But it's pretty far beyond our ability to observe anything, at least right now, with the instruments we have and the understanding we have. It's a lesson. All of this, I think, is not just lots of exciting, interesting surprises, but it's a lesson in humility. We shouldn't think that we understand things that we haven't measured.
Exactly, and I think in exoplanets we also get many surprises from observations that are like, who ordered that?
Right.
Another question, actually, a few people said were interested in that. Can you say anything about flybys of Jupiter moons? Is
Yes.
there any plan for that?
Yes, so we've just started our extended mission, and our extended mission makes use of the inner moons, starting with Ganymede, to shift the orbit a little bit, and includes close flybys of Ganymede, Europa, and Io. Now, remember, our instruments were designed to study Jupiter, so we're going to get a different look at Ganymede, Europa, and Io than previous spacecraft, sometimes better, sometimes worse. But we've just had a close fly of Ganymede. If you come to probably AGU is the conference where we'll be ready to talk about that in at least some detail. We can tell you what we learned at Ganymede, and then in a year or two, we'll fly by Europa and then eventually Io, and we hope to learn a lot about the surface of Europa. We hope to do some sort of advanced work that will help the Europa Clipper mission when it gets there, or the JUICE mission when it studies Ganymede. So yes, we're going to do flybys, and details of what we do obviously are determined by the abilities of the spacecraft and by funding and so forth.
Any other plans for the extended mission?
Yeah, so the extended mission is going to be, I'm going to go all the way back to my first slide because I mentioned it a little bit on there. The extended mission is going to be similar in terms of the orbit, but we're using the moons to shorten the period of the orbit. And then Jupiter itself, whether we like it or not, is moving perigove from near the equator where we started north by a little less than a degree with each orbit. So what that means is, as far as studying Jupiter goes, we'll get much of the same data we got, but the best data, instead of being near the equator, will be nearer to the North Pole. So we can study those circumpolar cyclones towards the end of the extended mission. We can look at the region where the belts and zones end and the Northern Hemisphere cyclone, more random looking structure begins. We can try to get further gravity data and look for the core or more details about the core. We can look for tidal effects in the gravity. we can do a more detailed map of the magnetic field, and we're going to devote some orbits to studying the great blue spot and try to understand what's going on there. We're fortunate that our perijove is moving north, because in a lot of ways the northern hemisphere is more interesting with all of that structure in the magnetic field. So the two big things that'll be different about the extended mission, lots of smaller things, but the two big things are getting a better close-up view of the north of Jupiter and doing those flybys of the moons. There's other things. We'll get some occultations. The spacecraft's going to go behind Jupiter a little bit. We'll see different viewpoint with respect to the sun, which is interesting. We get some of our best data for a lot of purposes when the plane of the orbit is perpendicular to the line of sight, or nearly so. And we will get that again as Jupiter's motion around the sun takes us around over the next few years. We'll go back to that orientation of the orbit. So lots of interesting things for extended mission.
I should have mentioned that the question about extended mission were from Laszlo Molnar and James Davenport, Stephanie Douglas, and also David Ciardi. They wanted to ask about the influence or the impact of the impact on the core. Why would the impact make the core less or more diluted? Wouldn't the core change after the impact if it got diluted?
So it's a question of time. As I understand it, the model that people are working with to base the core on a giant impact would be that fairly early in the formation of Jupiter, but late enough so that large objects had started to form, so the planetary formation was well underway in the solar system. There was an impact of something large, but not huge compared to Jupiter. So a mass of, I don't know, 10, 20, 30% of Jupiter's mass. And that, of course, would disrupt things dramatically. And a few billion years is not enough time for it to settle down again. The scale of Jupiter makes a lot of our intuition suspect. And one of the things we run into quite frequently is timescales like that. You look at the atmosphere and you see all the asymmetries and so forth, or the great red spot, and you say, how can that be stable? Well, it doesn't have to be stable. It only has to be stable on a puny little timescale of a human lifetime for it to look the way it does. And that sort of thing comes out when you try to work the numbers for how long would it take for Jupiter to settle down after that impact. The people who are working on this model, and it's not me, have suggested that, yeah, you can actually look at the timescale and it would not have settled down all the way to a core down in the middle by now.
Yeah, again, humility.
Yeah.
Okay, another question from Yuta Notsu. And again, apologies for any mispronunciation of any of the names. Would the aurora activity, is that expected to have some kind of time, like modulations over time or long-term modulations?
Certainly, we see lots of short-term modulations over the rotation period of Jupiter, over the orbital period of Jupiter, over fluctuations in the volcanoes and the solar wind and so forth. I think what he's asking, or what you're asking about, is long-term variations on a time scale of the planet. And the answer there is, I don't know. I would guess, and not my field of expertise, but I would guess that because we know the magnetic field is shifting on timescales short compared to the lifetime of the planet, I would expect the aurora to shift on those timescales. They're very ordered by the magnetic field. Almost every structure you see in the aurora maps back to something interesting using magnetic field line to do the mapping. So if the magnetic field is shifting around, sheared by the winds, then the aurora must be shifting around, sheared by the winds. but I'll say frankly, I'm making that up on the spot right now.
Another question by Alex Hindle. There are a number of vortices, or what looks like vortices, in the North Pole and the South Pole.
Yes.
They're not the same number in each pole, right?
Right.
So what do we know more or less? What determines that? And maybe it's also an issue of time scale. We check it 100 years in the future and it will all look different.
So the short answer is no, we don't really know what's going on, but we're starting to make sense of it. It's was well known. Simple predictions predict, or simple models predict, that cyclones should drift north and south. And a rapidly rotating planet like this, if you have a cyclone at mid latitudes, it ought to drift up to the North Pole or south to the South Pole. So it's not surprising that cyclones pile up at the North and South Pole. What's hard to explain, or harder to explain, is why there are 8 surrounding a central cyclone in the north and only 5 surrounding a central cyclone in the south, why that's stable, why the cyclones last as long as they do, why they don't eat each other up. So the models that people have presented and experimental evidence observations starting to support these are that the cyclones don't eat each other up because there's actually a central vorticity in one direction surrounded by vorticity in the opposite direction. Each of the cyclones sort of has a shield around it of oppositely rotating gas. You then have to explain where that comes from, and that's, shall we say, not well understood or not totally accepted that it's understood. Then you have to say, well, why, if that allows them to last a long time and not bang into each other without getting eaten up, why do we have a different number at the north and south? There are papers, there's work being done on that, having to do with the size of the cyclones, and you can model what that ought to look like. But then, of course, you're still left with, well, why do they have the size that they do? So what I would say is it's work in progress. The people who model these things are very excited about it and working on it. I mean, some of them are on our team and they're making good progress, and we're looking at what kind of data we need to support or contradict those models. We have the ability, as we get further north, at least in the northern hemisphere, to look at some of these cyclones at greater depth and see what's happening at a few hundred bars instead of just at a bar or two up at the surface. So it's a long-winded way of saying we have ideas, we don't know for sure, and stay tuned.
Next question, and you probably can hear on my Slack the question coming in. There are many questions, so I apologize for people. I'm only selecting a few. So I apologize if I'm not selecting your favorite question. An interesting question by Victoria Antucci. If someone would tell you you can build a Juno 2 mission, what would you put there? Would it be a clone, or would it be something, given the information you already have, would you put other instruments there?
Yeah, that's a really interesting question. And I would say...
And we are not providing the funding in any way. Purely hypothetical.
Well, the microwave radiometer, which was an innovation for Juno, has been tremendously useful, but we now think we know how to build it a little better. So one thing I would do would be to put a microwave radiometer on board that had the ability to steer the beam, maybe more frequency resolution, things like that. Essentially a more powerful microwave instrument. I don't think we could have built one back in any more powerful than we did under the constraints we had back in the time that we built Juno, but it's one of those things that can ride the wave of improving electronics capability. And so we now think we could build a better microwave radiometer than what was able to fly with a launch in 2011. I don't think, off the top of my head at least, I can't think of an instrument that I wish we had. Well, actually, one thing I wish we had on board that we talked about early in the mission, but didn't propose, and then we went to NASA afterwards and they didn't want to add it without, after the proposal, outside of the process, was a dosimeter. That's not so much for us, but it's for Europa Clipper and the European JUICE mission. So our spacecraft is built like an armored tank to withstand the radiation fields at Jupiter, and that's worked very well. But we also have not added as much as we perhaps could have to our knowledge about that radiation environment, which is more of an engineering issue than a science one. There's science there as well, of course, but it would have been quite beneficial to Europa Clipper and the JUICE mission if we were able to give dosimeter measurements that were measured, with them in mind. And we knew those missions were potentially coming before we launched the spacecraft, but not really early enough to include anything in the proposal. So we don't have a dosimeter on board. That I would do differently.
Maybe you can explain to me and everyone else what's a dosimeter. What does it measure?
So we measure the particles that hit the spacecraft in a variety of ways for science purposes. But what you want to do for science purposes is a bit different from measuring essentially the damage that it's going to cause to the electronics. So if you really are interested in, measuring things to protect future spacecraft, what you want is something that approximates what happens to electronics on a spacecraft. So you'd like little detectors that are electronics chips where they're damaged in a known way by radiation, and you surround them by shielding, by essentially bits of metal, but with different depths, so that as the spacecraft goes through the environment, you can see the damage, and you can see the damage on an axis compared with the depth of metal that's protecting it, and you get a real measurement of what one has to do to protect the next spacecraft from the environment. We're flying in a different environment than the JUICE or Europa Clipper missions, because they are equatorial and we're going over the poles. But we fly through the equator, and as we get late in the mission, we fly through the equator at a distance from Jupiter that's about right for them. We're learning things, and we'll pass along all the knowledge we learned, but we didn't bring along an instrument designed specifically for that purpose. And we knew how to build one. It just wasn't a science priority, and it wasn't enough of a programmatic priority for somebody to say, here's a few $1 million to go build it.
And just to clarify, the radiation is due to the intense magnetic field that you are flying in, right?
Yeah,
especially at the poles, right?
Actually, the radiation, the worst is near the equator. So if I look, here's a picture. I'm going to play that little movie again. I don't know how well it shows over Zoom.
Sure, I think it shows okay.
So if you see our orbit, the magnetic field,
I see.
Right, it traps particles near the poles. Those field lines are open, so particles get lost to the atmosphere or to deep space. Yes, they can stream in from the solar wind, but that's not as strong as the radiation belts from particles, say, emitted from a volcano on Io, ionized by sunlight, and then trapped in the magnetic field so that they drift around as the planet rotates and stay there for a long time, gaining energy. So the strongest radiation belts, the most dangerous part, is near the equator, Jovian radius or two out from the planet. And previous missions have been smart about it and have stayed far away from that, so they didn't damage the spacecraft. We're either braver or dumber. What we chose to do is come in over the pole, missing most of it, dive in under the radiation belts so that we could get really close to the planet and yet not spend a lot of time in the intense radiation and then come out the other side. And that's going to limit the lifetime of the mission, but our shielding has been well enough designed, and the spacecraft well enough designed, that we've already lasted beyond the lifetime, the amount of radiation predicted, or at least beyond the number of orbits predicted for all of the hardware.
Yeah, that's definitely very different than, you know, orbiting the Earth and considering the radiation around our atmosphere.
Right.
Another question from Iskra Georgieva. The core composition, maybe you've mentioned it, and I apologize for that. Do we still think it's a completely hydrogen core composition, or is that view changed or is changing?
What I would say is the bulk of Jupiter still is hydrogen, helium. That hasn't changed. The composition of the planet overall, in sort of the majority of the material, nothing's new. The composition of the important details ranges from surprised to we don't know. One way of getting at the difference in the dense core would be to have some difference in the composition for the heaviest elements, right? A way of trying to explain the atmospheric variation might revolve around the amount of water. Water is a key element for understanding or key compound for understanding the formation. How much oxygen does Jupiter have? And it's a significant part of the atmosphere, but nowhere near as much as hydrogen and helium, of course. And we originally thought, when we thought that before we got there, that the atmosphere would look sort of like it does right at the equator in this picture and be more or less uniform, that we could use the temperature profile expected in a radiative transfer model and the measurements with the microwave radiometer and determine the water. But, and in fact, we've done that at the equator. We have a paper out that says how much water we think there is in the atmosphere at the equator from 2 to 4 degrees north. The problem is that the rest of the planet doesn't look like that. So you have to be a lot more cautious in interpreting what it says about the water. And you also have to worry about whether the water is different at a much greater depth than anybody thought. I mean, the prediction was below 20 bars or so, the water should be uniform with depth and with latitude, and you should be able to tell the total water content by getting a measurement below 20 bars. It's clear from this picture that that's naive. And so we have a lot of work to do to try to figure it out. And estimates of the water, of the global water, range from, you know, less than 1 times solar all the way up to 10 times solar. We still have work to do to get the global water out of this. As I say, we have an estimate at the equator of a few times solar, and I'm optimistic that we have within the data, if we can really understand how to use it well enough to get to extend that to other latitudes and to greater depth. But it remains to be seen. Not sure if I answered the question or not, so feel free to follow up if that wasn't quite what you were after.
All the information you're providing is very exciting and, and educational. Perhaps last question from Hans Jelsen about lightning. Can the lightning inside the atmosphere change the chemistry? Can it, you know, jumpstart some, or like lightning in any atmosphere can do some chemical reaction, and then you might get new molecules?
So I want to give 2 answers. The first is I don't know, and the second is yes, of course. So I don't know because I haven't looked at that. There may well be people who have looked at that, but if so, I haven't spoken to them about it. And then, yes, of course, because as the question itself pointed out, we know that that happens elsewhere. There have been studies, so it seems like it's highly likely that if we go look at could the lightning change the chemistry, at least locally, it must be able to do that. But I don't actually know. I haven't done it.
Okay, I think this is a good time to stop, and thank you, Stephan, for doing this. I learned a lot, and I'm sure many other people learned a lot. As someone working on exoplanets, it's a completely different ballgame when you're trying to fly over and learn about the planet from up close. And I really like your what you opened up with humility. That's we need to be reminded of that from time to time.
I think that's important for all of us. I will, because I didn't get a chance to mention, I will say if you go to if you Google Mission Juno, all one word, you'll find our website. There's a lot of stuff there for citizen science opportunities and educational things that I didn't even talk about that are also really fun and interesting and exciting.
We do have another minute or two if you want to mention a little bit about that.
Sure. Okay. So we have a visible light camera on the spacecraft called Juno Cam. And we put it on the spacecraft for education and outreach without a science team. What we do is we take very close to the raw data, we dump it out on a website, and we invite the world to play with the data and make pictures. And they've done a phenomenal job. If you go to Mission Juno and look at the pictures made by citizen scientists, by amateurs, by artists using the JunoCam data, it's just absolutely amazing. Since that time, there's also science coming out of it. Some of it from the amateurs. There are now papers published in peer-reviewed journals led by people whose involvement with Juno is only that, you know, they're not professional scientists, but they were interested and they learned about it and figured out how to do science with it. There's lots of combinations of, you know, teaming with that, and a huge collection of people doing Earth-based observations tied into Juno. So that's what we're taking a look at. And I also say on the more classroom education side, we have a partnership with GAVRT, the Goldstone Apple Valley Radio Telescope Project, in which students use a radio telescope and collect and analyze science data and do real science. And one of the things they're doing is observing Jupiter in support of the Juno mission.
Sounds a lot of fun, that Juno camp.
Yeah, it is.
I'll look it up. Okay, so we can finish here. Thank you again for doing this, Stephan.
My pleasure.
For the audience, a few quick messages. The next session in the conference will start today at 3:30 Eastern Time, 7:30 UT, 9:30 p.m. Central European Time, or 12:30 on the North America West Coast. We will start with a panel discussion about young stars, and then we will have two talks related to young stars, and then we will have a 1-hour parallel session, one about exoplanets, the other about stellar astrophysics. That will happen later today. That will be session number 6 of the conference. Another thing happening today, it is not related to the conference, but I will quickly share my screen to advertise that. I hope you can see it. This is a little over an hour from now. The EPRV, the Extreme Precision RV Radio Velocity Working Group, has issued its final report, but we'll also have like a live event. This is, as you can see, 2 p.m. on the East Coast, 11 a.m. on the West Coast in the Pacific time. And more information about that you can find in the Exoplanets channel on the Slack, on the conference Slack workspace. And with that, I think we can adjourn this session. Thank you everyone for joining, and see you in the next session.